Today, large language model is everywhere and its importance in the data engineering and the other data domains is growing rapidly. Now you will say, Ansh, we also want to master LLM, but we do not have any prior knowledge, we do not have any prior experience, and we do not have any kind of resources. That's why I have created this complete large language model course so that you do not need to worry at all. This course will take you from zero and will make you the hero of the large language model world. And you will master all the inner workings of LLM along with all the code examples plus practical demonstrations as well. And yes, we gonna just go much deeper in the LLMs. But why I have created this video? After getting the great response on my generative AI full course for data engineers, I thought of creating a dedicated video on large language model as well, so that you all are aligned in this industry. And yes, your job is also AI proof. The best part, all the timestamps are attached with this video so that you can just skip any chapter if you already have some prior knowledge in that particular chapter. But yes, it's my responsibility to just take care of each individual. So that is why I have put all the fundamentals as well. So that means no prerequisite is required. So I can say that LLM full course for data engineers, or you can say for data domain, is finally here and it is for free. Wow. But I will really appreciate if you can just hit that subscribe button right now and just leave a lovely comment in the comment sections, because obviously I'm putting a lot of efforts to create these videos. And if you want me to continue this thing, so you can obviously motivate me by hitting that subscribe button. That's it. And now what are you waiting for? Let's get started with this amazing course.
So what's up, my fam? Happy Sunday. Happy Sunday. And finally, on your special request, large language models from zero to here zero to hero video is here. I know your request was 100% valid, because I realized this thing. Okay, generative AI fundamentals are important, and obviously there's a video created on that thing, generative AI fundamentals and generative AI full course. But I realized this thing on your special request, that we need to understand LLM in more depth. We need to know all the ins and outs, because when I created the generative AI full course, I obviously discussed about so many things. But when you actually requested for the right thing, I was like, okay, this request is actually valid. So let's create a dedicated video on large language models, because now from 2025 onwards, and it's almost 2026 now, industry has a great revolution. Okay, and it is welcoming so many new domains, so many new roles, and whatever. In everything you will see LLM integrated. Data engineering, LLM integrated. Data analytics, LLM integrated. Data science, obviously LLM integrated. AI, LLM integrated. Software engineering, LLM integrated. So everything is integrated with LLM nowadays. So you need to build that base. Why? So bro, when software engineering was really new, did you learn those languages? C++. Did you learn those things? How to create, how to write a loop, how to do all of these things? Why did you do that? Because you did all of those things in the past, you were able to crack the companies, you were able to be like, you were relevant in the industry, right? So now it is the best timing to know everything about LLMs, because this topic is new. Sooner you will just understand all the things around it, you will become an outlier in the crowd, and this is the best timing, and you do not need to miss this timing. Okay, and now obviously this video is there for you, so now you will understand everything. So the thing is, I know everyone tries to learn LLM, right? Because I know you all are hardworking, you all are very serious about their future. But LLM is not very easy to understand, because there are so many things: transformer, encoder-decoder, Encoder-Only, Decoder-Only, self-attention, QKV. There's so many things, I know. But I will make a promise to you right now, okay, to all of you. See, I will make you understand all of those things, everything. I know transformer is a very complex topic, but you will master it. Trust me, trust this guy. And in return, you will do me a favor. You will hit the subscribe button, okay? And you will drop a very lovely comment, okay? Promise? Pinky promise? Okay, so let's start. I will not take much of your time. Let me just tell you who should watch this video so that you are okay and you are free if this video is not for you. But let me just tell you who should watch this video. If you want to understand large language models, no matter what is your background, no matter if you are a student, if you are an employee, whatever, because LLM is new to everyone, even if you are, let's say, having 20 plus years of experience, or even if you are studying in the college, both have the similar experience with LLM, okay? Because LLM just appeared 1 to 2 years back, and now we have the better understanding of LLM because now it is mature. So this video is for everyone who wants to understand LLM, like what's going on, because everything nowadays are built on top of LLM. Your chat GPT, your Claude, your Perplexity, whatever, everything is built on top of LLM. If you want to understand it, this video is for you. Simple bro, simple. Okay. So now what is the agenda of this video? What will be the things we'll be learning? Okay, this video is on LLM, but what exactly we need to learn? Okay, bro. Okay, let me just tell you. So in this particular video, we're going to discuss so many things. Wow. Great list, right? To be honest, we're going to discuss so many more things as well, but I just mentioned these things. So first of all, we will just talking about NLP, which is the backbone of everything, natural language processing. Then we're going to talk about tokenization, which is the fundamental step of everything. Then we're going to talk about tokenizer. Okay, we will be just looking at some real tokenizers, OpenAI, tick tokenizer, everything. Then we're going to talk about embedding vectors. So here I want to make a point. You will say, Ansh, Lamba, we were supposed to ask one more question. What is the prerequisite for this video? So when I say embedding vectors, if I'm explaining even the embedding vectors in the video, that means there are no prerequisite. There are no prerequisite. Make sense? Now I will just take 1 minute because this 1 minute will make your whole video experience better. I know some of you will be already familiar with all these basic terms. For example, tokenization, tokenizer, embedding vectors. Some of you will be familiar with these terms. Feel free to directly skip these, you can say chapters, okay? Because I have provided the chapters in the timestamps. If you already know these concepts, I respect that thing and I respect your time as well. You can skip these chapters and you can directly jump on the chapter from where you want to learn. But my duty being your guide is I want to tell everything from scratch, right? Because there are so many people who do not even know tokenization, right? So we have to take those people as well and we need to help those people as well so that they can also grow in their life and obviously make their family members happy. Okay, sorted. So feel free to skip any chapter. There is no foundation to anything. But if you want to revise something, if you want to study that topic from me, anytime, bro, anytime, just do that chapter as well. But yeah, call is yours. Okay. So this video will save your time as well. No worries at all. Okay. So after learning about embedding vectors, we're going to talk about types of embedding vectors. Then we're going to talk about self-attention. And from here, things will become more and more complex. But Ansh, Lamba is here. So take a chill pill and just relax. Okay. So self-attention, then we're going to talk about QKV, that means query vector, key vector, value vector, which is the backbone of contextual embeddings. Then we're going to talk about softmax. Then we're going to talk about dimensions. Then we're going to talk about feed forward networks. Then we're going to talk about LM head, decoder-only architecture, encoder-only architecture, encoder-decoder architecture, and then finally GPT models, BERT models, and T5 models. Wow. So many technical terms. So many technical terms, bro. Do you know what? Now you are looking at these terms like this. What are these terms? But just give me this video, okay? Just allow me to complete this video. You will understand each and everything, and not will understand it. You will be able to absorb the knowledge and you will be able to perform the things in real life. Trust me. Okay. So this is the agenda of this video. Are you excited? You just need to take out your notebook because I know notes are provided in the GitHub repo. I know that all the things are provided in the GitHub repo. All the code examples are also provided in the GitHub repo that you can just take. But I would recommend you to just write down some things. Let's say 1 to 2 pages, 3 pages, please. And I know you are very rich. You can just take out your digital notebook, okay? And you can just take notes in that as well. But your choice. Okay, so let's start this video, and I just want to congratulate my lovely data fam because I love them a lot. So I will take just a few seconds to congratulate, and it will motivate you as well. So congratulations my lovely data fam who have recently cracked their offer letters. Some cracked their job offers with 200% hike. So proud of you, because these are my lovely data fam. Okay, these are my lovely data family members. And you will say, what did they do? What did they do? What did they do? So they didn't do anything special. They simply followed the guidance on this channel. Okay, and they were just learning throughout the journey, and they were able to crack the offers, and I'm very happy. So I want to congratulate. So congratulate all of you. 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 Anyone else? Okay, finally. Okay, and I might have missed some names. Okay, so do not feel bad, but congratulations to all of you if I missed your name. Okay, very good. So these are my social handles, and you can just simply follow me if you just want to. And obviously this YouTube channel is there for you. So without wasting any time, let's get started with this masterpiece, and I'm watching you. Okay, just take out your notebook and let's get started. So we need to start our lecture, or basically this amazing masterclass with this concept. A lot of you would have already heard about this term. It is called NLP. It is called natural language processing. What is it called? Natural language processing. So just remember one thing. Okay, this is a very fundamental thing, but you should be aware of this. The thing is, if we talk about LLMs, whatever we are using right now in the industry, ChatGPT, Claude, anything, all those famous web chatbots that are built on top of LLMs, the backbone of everything is NLP, natural language processing. What exactly is NLP? If we just want to quickly and briefly cover this topic. So basically NLP is a subfield of AI that focuses on developing technologies that are capable of understanding, interpreting, and generating human language. What does it mean? So NLP is a kind of special computer program which can understand what I am saying right now, which can interpret my feelings, like not exactly feelings, but in what context I am saying something. So interpreting, and it can generate the same thing, same response in the same language. This is NLP in a nutshell. Make sense? Because AI is so wide. Okay, there are so many areas, there are so many subdomains within AI. NLP is one of those subdomains, or you can say subfields of AI. Make sense? Which is purely focused on processing our natural language, processing what I'm saying right now, processing and generating the same thing in the same language or in other language if I just ask it to. So in short, NLP is a computer program that can work with our normal language. That's it. That is it. Because usually what we do, let's say I want to write a program, right? Let's say I want to print numbers from 1 to 100. So what I will do, let's say I'm using a Python. So forget about Python. First of all, let's say this is me. Okay. Let's say this is me. Okay. And this is my computer. And I want it to generate numbers from 1 to 100. So what I will do, I will say, bro, I want you to generate numbers from 1 to 100. And this will say, what are you saying, bro? I don't understand. So then you will write a specific language. It can be any programming language. It can be Python. It can be C++. It can be Java. It can be anything. So you will write something like this. Let's say, let's use Python. So you will write for in, let's say range 100, or let's say 1 till 101 because it is explicit. So you will simply say print I. So what did you just, what have you done just now? What have you done? You have simply talked to computer, okay? You have simply talked to this computer with this language. Why? Because computer can understand this language. Really? Yes, because it has interpreters, it has compilers, it has everything that it needs to understand this language, because obviously computer can understand only zeros and ones. Okay, it simply understands zeros and ones. Make sense? But it can understand this language as well because it has compilers, it has interpreters, it has all those systems. Oh, so whenever we want to talk to computer, whenever we just want computer to do our work, we have to talk to it using programming language. Now in today's era, we are one step ahead. If I want this computer to generate me the numbers from 1 to 100, I can literally say like this. Literally say like this. Let's say, I will say, bro, please generate numbers from 1 to 100. And you will say, bro, are you serious? Are you serious? I am serious. Let's say this is my computer, and if I simply pass this language, it will generate this thing. Why? Because of advancements and the success of NLP, that is natural language processing, in today's era. In today's era, we don't worry, you will understand everything. Everything, like how does it working right now, LLMs, how they are just playing, because the backbone of this thing is LLM right now. Okay, you will learn that as well, but this is like very fundamental thing, because I want to cover everything from scratch. Okay, literally from scratch. So make sense? Okay, so let me just show you a quick example of it. You will say, I don't believe, like, is it true or not? So I can literally show you the example. So let me just bring my, let's say, any ChatGPT, any browser. So I will literally say, stay logged out. Please, or let's use the same example, bro, generate the numbers from 1 to 100. So now what it did, it literally generated the numbers from 1 to 100. Did I write any Python code? Did I write any C++ code? Did I write any kind of machine code? Literally nothing. What I did, I simply used my natural language with my natural accent. I literally used bro. Can you imagine? This is the power of NLP. And just to be more specific, this is the power of LLM, large language models. We will be just talking about that as well, but this is just a kind of high level overview. So can we say that in future we can code using our natural languages? See, nothing is impossible. Okay, first of all, this thing. And second thing, Nvidia's CEO has already said that in the near future, or maybe in the next 5 to 10 years, people will be doing programming using natural languages. So this was his statement. Okay, and if he would have made this statement 10 years before, everyone would be laughing at him. But now when he made the statement in today's era, in LLM's era, I don't think so it's a big deal. We can easily work with natural languages to directly talk to the computers. It's not a big deal now, because now the innovative curve is growing rapidly. Okay, see, literally I didn't write any kind of Python code. So I know behind the scenes it will be just converting this text, and it will be generating a Python code under the shell. Okay, and then it will be just running a Python code in a compiler, and it is just generating simply the numbers. I know this, but in the near future, I think there is not even a need to convert this text into code. It will directly convert this language into machine code. This is my interpretation. Let's see how it goes, and it will be very, very fun, right? And don't worry, you will get all the updates on this channel. Okay, everything, all the learnings, all the tutorials, everything. This channel is there for you, for your path of success. Okay, so just hit the subscribe button right now, and let's continue with our lecture. So this was all about NLP, which is the backbone of everything. Now obviously we are focusing on learning and understanding everything related to large language models. So now it's time to be more specific. And before even talking about LLM, we first need to talk about language model. And I am so sure that you would have heard about these definitions a lot. Large language models are just language models, and they are just trained on the large data set. Bro, this is an incomplete statement, and this is an incomplete definition. I know this is confusing. When I was learning all of these things, I was also confused. I was like, Maybe this will be the definition, but when I just dig deeper, I was like, bro, this is not the real definition. So let me just tell you what exactly is language model, and then we will be just talking about what is a large language model. Language model is the fundamental unit of large language model. This is the starting point of large language model. Make sense? Just for a few minutes, let's forget about forget about everything related to large language models. Let's only focus on language model. What exactly is language model? And do you know what? You will be like blown up with this fact that language model is not actually a model. It is more of a concept. Are you serious? Yes, I am serious. Language model is more like a concept, is more like an architecture. It is not basically a rule. This is not a specific model. This is a concept. Language model is a concept. I was also blown up when I was just reading this, but this is true. Okay, so what do I mean? So first of all, let's cover the definition. So basically, language model is any model. It is not restricted to any specific model. It can be any model. And model is what? Any program, any computer program that learns to predict the next word or token. That's it. So if let's say you have created a computer program, and if you are able to predict the next word, then I can say that you have built a language model. And I'm not kidding. I am not kidding. Why? Because this is true. Language model is any computer program, is any model that can predict the next word by using the previous words. Now, one thing can be confusing. What is token? What is word? Obviously, we're gonna just learn everything technically as well, like what are all these words. But for now, you can imagine that word is equivalent to token. Okay. By the way, both are not same, but to some extent they are same. We will be just talking about tokenization, everything. Don't worry about that. But this is the concept. For now, you can imagine word is equivalent to token. Okay. Good. So let's say you are writing something. Okay, so, and you would have experienced this as well because this is very common nowadays. Let's say you are writing an email, and if you have not written an email in your life, or if you have written an email but you didn't actually observe this thing. So I will ask you to just open your any favorite email manager, Gmail, Outlook, and just start typing something. Okay, just do it right now parallelly. Okay, in your mobile phone, in anything. Opened? I hope that you have opened your email browser. Just open it, bro. Like, you will learn better. Trust me. So now what you need to do, just start typing something like this. Let's say, good morning or whatever. Okay. Good morning. Okay. And then you will say, this is, and suddenly you will see a suggestion in the grade text, and it will be something like this. Let's say, regarding, like this. Are you getting this? Or maybe something else, because it depends like what you have used, because it is like obviously customized based on the user preference as well. But you will receive something here after typing this good morning, this is, and you will get some suggestion here, right? You will get some suggestion. What is this thing? This is language model. Really, this is a language model. So now what is happening, whenever you are just typing something, okay, so you are literally providing some words or tokens, okay, to your next token. For example, you type this, okay. Now language model will predict this word on the basis of this input. Good morning dot this is, and then regarding. And then let's say you selected this. Let's say you selected this. You hit tab and you wrote this regarding. And then you can simply say this is regarding something like that. Let's say regarding a ticket, something like this. Okay, something regarding and then you will receive something else as well. Let's say you will receive something like this. Let's say ticket. Okay, you will receive something like this. Not exactly ticket, but something. So what is this? Now this model is using this whole as the input. Again, we will just talk about this as well. Will it use the whole as a input or not? Okay, but for now you can imagine that this will use this whole as the input and it will predict the next token, next word basically. That is the entire work of the language model. That's it. That is it. So that's how you are getting suggestions while writing an email. How it is doing? It is not a magic. It is actually using the language model or whatever program they have made, they have built. And obviously this model is trained, any model is trained on some data. Obviously, if you have just worked with any ML models, those very basic models, if you have built in your college days, let's say building regression analysis, building k-means clustering, all those things. I still remember, like in my college days, I built the project called laptop price prediction. So yeah, so everything needs to be trained, right? Again, I'm not saying like you need to know machine learning concepts. No. I'm simply asking you to relate it to something which is related to training. Any model requires training because you need to feed the data to train a model. That's it. I'm not expecting you to do all of those projects and analysis. No, it's fine. Okay, because you do not need to reinvent the wheel. You do not need to build a language model. You do not need to build a large language model. You need to use it because large language models are already there for you. Those big tech giants have spent billions of dollars to make those models and now obviously spending more and more to make it more scalable. So you do not need to compete with those big giants to create your own LLM. No, it is quite next to impossible because you need so much of money, so much of computation, so much of everything to build that particular highly scalable large language model. But you need to know the concept. You need to, if you know the concept, then you will be able to efficiently use those LLMs. Okay. So this is all about a language model. In short, language model will just predict the next word. Make sense? On the basis of the previous words. Okay, makes sense. So can I say this thing? What thing? This thing. The core objective of the language model is probability of next token on the basis of the previous token. And if you are unaware of this thing, have you ever studied something called as Bayes theorem in your school? In the chapter number 16th of probability, I guess, or 15th of, I think, class 11th or 12th. I don't know. But yeah, you would have studied this in your school if you would have taken mathematics. I'm not asking you to just study Bayes theorem. What is that? But this is very much similar to that thing, which is called conditional probability. That means we are just trying to find the probability of next token on the basis of the previous tokens. Make sense? Make sense? By the way, probability was like one of my favorite chapters because it was like so much of fun. It was fun. So we just need to find the probability of next token on the basis of previous tokens. And let me just check like Bayes theorem chapter. I think if you are from like NCERT background, I would say it was in 11th or 12th. Probability chapter mathematics, chapter number 14. Oh yeah. Because I remember like it was at the end of the book. NCERT. Yeah, chapter 14. Yep. Okay. We do not need to study this, but yeah, it was fun. In class 11th. Okay, remember. Okay, fun. So this is like the whole context of, you can say, language model, not large language model, simply language model. Make sense? That is why mathematics is important for AI world. People say like, you do not need to know mathematics, you do not need to know statistics. See, you do not need to solve something. You do not need to solve trigonometry solutions. You do not need to find you can say hypnotis. What is that? Hypnotis? Wait. 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 H square equals to a square plus b square. Okay. What is that thing which is slant? H. something called as, I forgot the name. Okay, just Google it. Let's do it. It's called Pythagoras theorem. I forgot the name. Oh man. Pythagoras theorem. Hypno 2 something like that. Oh man. Hypotenuse. Oh man. See, that's how you forget the things. But yeah, so I was saying, like, you do not need to solve those questions. But when you know these things, probability, binomial distribution, you can say outliers, standard deviations, all of these things make some sense when you're just trying to build a solution which actually solves the problem. Make sense? So you do not need to be a pro mathematician or statistician, but some basic school level understanding is enough. Literally enough. You do not need to do PhD in these things, but just a quick, you can say, revision will be enough. Okay, so do not worry about mathematics and statistics much, but consider those things. Those are important. Okay, so this core objective is also done. Now let's actually see the types of language models. You will say, Ansh, Lamba, we need to focus more on large language models. Okay, and why are we studying about types of language models? What if I say that large language model is just one of the types of language models? Literally, yes. Oh, this will be fun then. Yes, this will be fun. So let me just tell you types, basically types or evolution, like how things change with the time. So what I said before, language model is more like a concept. We need to achieve a goal which will only predict the next word. Make sense? Very good. So it all started in iterations, and I would say it all improved in iterations, because not like in one go you just made the perfect large language model. No, it actually evolved with time. So the first thing was stats era. So what is this stats era, or basically you can say statistics era? Initially we started predicting the next word with a technique called n-grams, and we still use it in so many applications. So that is why each type is important, but large language model is the most hyped and popular one right now. Okay, but you need to know these things. So now what was happening, we were using a techniques called n-grams. What is this n-gram? So these are like terms, bigrams, trigrams, on quadgrams, all those grams. What are these grams? Let me just explain this, because once you understand this, you will be like, okay, now I know like how this thing is just doing all the things. So let me just open my rough notebook. Okay, perfect. So now let me just tell you n-grams. Let's say my n-gram size is 2, and we just usually call it as bigrams. Okay, bigrams mean like 2 grams. Okay, 2 grams. So what I will do, I will train my data. Remember our example? So our example was good morning, this is, okay, or let's say, let's take bigram or trigram, whatever, it's your choice. Okay, so now I was getting a suggestion for regarding. Okay, do you know how it is due to, let's say we are using statistics era. We are in the statistics era, and we are using gran or n-gran technique to predict the next word. Okay, so how I will receive this regarding? By just using the previous token or previous word. Really? Yes. Okay, so how it is able to do that? So basically, when we just train our model, or when we would have trained this model and this bigram model, so what we would have done, we would have provided a large corpus of text using Wikipedia or whatever, and we literally created pairs of text. Basically, let's say good morning, this is regarding a, and blah blah blah. So let's say this is one pair. Okay, then this is second pair. Okay, then this is third pair. Okay, then this is fourth pair. And now when I was just writing this is, so most probably language model, this bygran model said, bro, just put regarding. Why? Because I am already trained on this kind of model, this kind of text, and I know like the most suitable word is regarding after is based on these bygrams. See, good morning, morning these, and this is, and then finally is regarding. Now is regarding is coming directly from the previous word and based on the, you can say, text that it is trained on. All the Wikipedia text, all those great, you can say, research papers, everything. It is trained on some text, right? This is called bygran. Now you can just change the you can say strategy, trigran, maybe you are just training the model on 3 things. So that is how you are just getting the word, a suggestion, which is not very accurate, which is not very useful, but still you will get something. Why? Because its duty is to predict the next word. That's it. Most of the time you will get the word which is useful because it is trained on so much of data, so it knows like how to just give the next word. Make sense? Then let's say you use this word regarding. So what will happen? It would have been trained on the word called regarding A. So it will say next just predict the word called A, like this. And then it would have trained on the data which says a ticket. So it will simply say next word is ticket. So this will keep on going as you'll be just keep on typing. This is called n-gram technique. Make sense? This is called n-gram technique. Okay. This is still in use, so do not feel like it is outdated completely. No. Next we have neural era. This was very popular around, you can say, 2013 till 2016, 17. Very popular, very popular. And neural era, this was using RNN. Okay, this was using RNN. Basically this was like purely built on the neural networks. It was one of the hit techniques to build the language model. Why? Because it was using something, a very good example is word-to-vec. Word-to-vec was developed by Google. Okay, because obviously in the Google search engines you use so many things which require NLP, something called as translation, all those things, right? So word-to-vec was created by Google and it was one of the biggest hit technique at that time using language models. Okay, so what it was doing actually, it was able to find the meaning of each single word, and that was a game-changing thing. Literally, like if you're writing good morning, it knows the meaning of good, it knows the meaning of morning, it knows the meaning of this, is, everything. It knows the meaning of each word. It was using something called as dimensions. Initially it used 300 dimensions. Don't worry, you will get the better understanding while we will be just discussing about how to create embeddings. Okay, do not worry about that. So 300 dimensions embedding, basically let's say your word morning will be evaluated against those 300 features and it will get a score, it will get a vector. Okay, so it will be converted into a meaning. It was a great hit product, but not a product, like basically a technique you can say, but it was not very efficient because it was processing the text in sequence, like one by one. No parallel computation is there, nothing. And there were like so many other flaws as well that we will just talking about when we will be just discussing about LLMs that solve the problem. Okay, so this was about neural era. Then let's finally talk about transformers. This is the current era. This is the current era and this is your LLM. This is your LLM. Make sense? So transformers changed the industry. They brought the revolution, real revolution. And you will actually see everything, like how they are just doing the things, but very high level overview. Transformers actually revolutionized this space and they made NLP Like so useful in today's era. Like literally you can do anything using your language, and you are doing actually. You are using ChatGPT for everything, right? How we are able to do that? LLM transformers. There's an LLM behind it. There's an LLM behind it, behind ChatGPT. It is called GPT model. GPT model is an LLM. Make sense? So this is your current era, and this is like developed. This was developed, I think, in 2017 when we got the research paper called "Attention is All You Need." Okay, this was there, I think, in 2013, and this was there, I think, around early 2000s. So yeah, this is the journey so far. So these are the types of language models, and this is one of the type. So you can literally say LLM is just one of the types of language models, because language model means we need to predict the next word. We can use this thing to predict the next word. We can use this thing to predict the next word. We can use transformers to predict the next word. So that means LLM is just one of the types of language models. Do not just say when we just train the language models on large data set, it becomes large language model. No. That point is partially correct, that yes, we train our data on trillions of data sets. That is true. But it is not right way to say, hey, just train the language model on large data set, it will become a large language model. No. Large language model is one of the types of language model. It is one of the technique that we follow to build a language model, right? I hope now you have the clear understanding of language model. Okay. Now, obviously, we need to learn large language model in this particular video in detail. Okay. We know that, but first of all, let's actually start from very basics, like what exactly large language model is doing under the shell. Okay, let's see. So now let's talk about the large language models, because now you know, okay, what are language models. So now you can understand large language models better. And I think you have already understood the concept, but still it's time to have a quick look. So basically large language models in a nutshell are nothing but just the transformer based. This is important. And this is the backbone that we have discussed so far. Not every language model, but transformer based language model are called large language models. And as we know, which is very obvious, that large language models are trained at the massive scale. That means on billions of parameters, trillions of parameters, and so on. But the core idea is still predict the next token, and scale and architecture make all the difference. Make sense? So in short, large language model is not like any language model which is trained on the larger data set or any, you can say, billions of trillions of parameters. It is specifically transformer based language model. Make sense, everyone? Make sense? Okay, very good. So now let's see the types of large language models. Do we have types of large language model? Basically, do we have types of LLMs? Obviously, bro. And all of these LLMs are serving specific area. Let me just explain. So first of all, there are three major types of LLMs we have in the market. Okay. Encoder-Decoder, which was the very first LLM. Second is Encoder-Only. The third one is Decoder-Only. This is the most popular one, and this is the transformer that you are using right now. You are using, I'm not kidding, you are actually using this. How? If you're using ChatGPT, if you are using Gemini, if you are using any chatbot, okay, so any chatbot is obviously built on some kind of LLM, and that LLM is of type decoder only. How do I know? All the GPT models, GPT means, first of all, generative pre-trained transformers. Generative pre-trained transformers. All the GPT models, GPT-3, GPT blah blah 3.5, all of those GPT models are actually decoder only. In short, if any model is generating some text or anything, it is actually decoder only. You do not need to worry about encoder, decoder only, because that is why we have this video. We're going to discuss about the architecture in detail. But for now, You need to understand like there are these kinds of types, and these are some of the types. You can just call it as, let's say, X, Y, and Z. And X is called encoder-decoder, Y is called encoder-only, Z is called decoder-only. But I have already given you the heads up that GPT models are the most popular ones, and all those chat GPT, all those AI chatbots, whatever you are using right now is actually built on top of decoder-only. This is the most popular one, and you need to obviously understand all the three types in detail, because encoder-decoder was the primary one, and encoder-decoder is actually used in very specific areas. For example, why do we use encoder-decoder? We use encoder-decoder, in short, okay, where we need to use or basically utilize input and need to make sure that we can also generate the text. For example, translations. So whenever you want to translate our text, let's say I'm just speaking in English, you need to just translate it into, let's say, Telugu. You need to translate it in French. You need to translate it in Hindi, any language. So all those translation based models are T5 models. That means encoder-decoder. Oh, okay. What are encoder-only? Encoder-only models are used when you just want to understand your input. What do I mean? For example, I asked something. Let's say let me write a question. Let's say, what is temperature? Or let's say, what is anything? What is a bike? Let's say there's a 5th grade, 4th grade. I think 4th grade student would know what is bike. Let's say 1st grade student would also know. Like, let's say 3 years old. 3 years old do chat GPT? Maybe in future. So let's say there's someone who doesn't know about a bike. Okay, what is a bike? So I wrote this question, what is a bike? So now I don't want to generate any answer. I do not want to do that thing. I just want to understand this. I just want to make something which will hold the, you can say, value of this particular input, richer value. So that is where encoder-only models come into the picture, and we will be just using that as well. I will just show you how you can just also use it. Obviously it would require some API calls. Okay, so if you do not have API setup, you can set up. If you do not want to, you can still refer my notebook just for the understanding, because you first need to understand the stuff, then you can just do the coding part as well. Coding part is not very important, but when you will see the code, you will understand, okay, that's how it works. Okay, makes sense. So do not need to worry, I'll just show you both the things. So just relax. Okay, so encoder only means we just need to understand it. We do not want to generate anything. Decoder only says my primary goal is to generate. Chat GPT's primary goal is to generate the answer. That is decoder only. Make sense? Ansh, Lamba, a quick question. Yeah. When you say decoder only, you are saying that its primary goal is to generate the text. Correct. But how it will understand the input? Because obviously before generating something, it needs to understand something, right? And we do not have any kind of encoder here. So how it will understand the context, or how it will just understand the input? Very good question. So decoder only has some architecture, has some areas where it can just understand the context. Okay, it is called masked self-attention. Okay, this is a technical term for now, but very soon you will be mastering this term. But it has something which can be used to understand the context, but not as richer as this encoders, because this doesn't have any kind of encoders, right? So understanding will not be very rich, but still will be good enough to generate the text. Make sense? Good. I know you have so many questions and you're really excited to know all of these things. That's the thing. This area is very interesting, because this is so new, right? We didn't actually imagine these things would be happening, and this is now actually happening. So yeah, I know. So hold your breath. I am here to explain you everything. Okay, don't worry, I'm here with you. So now you understood LLMs. Okay, encoder-decoder, encoder-only, and decoder-only. Now we need to go deeper and see the architecture and everything. Before going into this, you need to know just two things. One is tokenization. Remember, I said like for now you can just imagine that word is equivalent to token, but actually it is not. So first thing you need to understand about tokens and tokenization, because tokenization is a process where your text will be broken down into small tokens. Okay, first thing. Second thing, you need to understand embeddings. Okay, so first let's cover tokenization, and then we will just understanding embeddings. Then we will be just going deeper inside the architecture, because these are the two areas that you need to know. Okay, and while discussing the embeddings, you will be actually working with encoder-only. Okay, encoder-only transformer. So you will actually write the code. Don't worry, you will actually write the code. Imagine. Okay, so let's see. Okay, and now let me just take you to a website and let's quickly talk about tokenization. Okay, so now let's talk about the tokenization and token ID. This is the very first step. Okay, whenever you just want to work with any LLM. Okay, literally very first step. What is tokenization? You already have some kind of understanding. Like, we just break down our input into smaller tokens. Yes, that's true. And literally this is all about tokenization. So tokenization is the process of breaking down text into smaller units, and we just call it as tokens. You will say, Ansh, Lamba. Yes, sir. So why can't we break down our text into words? What's wrong with that? See, we have to consider all the scenarios. Sometimes one single word is actually made up of so many small words. Make sense? Let's say pre-trained. Pre-trained is not actually one single word, but when we write it as a single word. So it affects like how model should process the data. In most of the scenarios, like I would say 60% of the time, your token will be equivalent to the word, but 40% of the time it will break down that word into smaller tokens. Don't worry, Ansh Lamba will show you the practical as well. Okay, so do not feel like we are not seeing the practical. We will see it, but first try to understand the concept. Okay, good. So tokenization is the process of breaking down the text into smaller units called tokens. So whenever you need to work in the AI field, we do not call it as like broken down into words. We call it as like it is broken down in the form of tokens. Okay, so these tokens can be words, as I just mentioned, but these tokens can also be the subwords. Okay, like subwords. These tokens can also be the characters. Let's say hyphen, comma. These can also be the tokens, obviously, because whenever we are writing something, comma, hyphen, these actually change the meaning. Makes sense. That is true, right? Or even the sentences. Yes, sometimes we just consider the whole sentence as a token. It all depends upon how the vocabulary is for that particular model. Make sense? Depending on the level of granularity required for the specific application. But in most of the cases nowadays, we do not consider the whole sentence as a token. Earlier it used to be, but now words, subwords, and characters. Make sense? Now, okay, tokenization is understood, and I can also show you a quick example of it. Let's say I am writing a sentence that my name is Ansh Lamba. Okay, or let's say I want to provide some input, any input, so that it can understand something, right? So let's say I want to code. Okay, I want to code. So now this sentence, I want to code, will be broken down into tokens. So let's say one token will be I, then second token will be want, third token will be to, fourth token will be code. So this way, this will be broken down into the tokens. Now luckily, or you can say coincidentally, we will be having one single token for each word, because these are very common and very basic words. But sometimes when you, let's say, are writing something, let's say I am coding, so maybe code will get a different token and ing will get a different token. Let's say you can write I want to code applications. So application will get a different token and S will get a different token. It is possible. It is possible. But it all depends. Okay. So this is the tokenization. But what is this token ID? What is this token ID? So bro, let me just tell you about what is this token ID. So whenever we just talk about this whole process, breaking down the sentence in the form of tokens is just the one step of it. And there are like actually two steps involved. The second step is assigning the token ID. So there's one more step involved after breaking down the text into tokens, which is converting these tokens into numerical representations like token IDs. We are not talking about here embeddings because I know some of you are already aware of some fundamentals. So do not be confused. These are not embeddings. These are just converting those textual tokens into some numerical value, any numerical value which is set by the model itself. Okay. Because whenever we need to pass something to the model, it needs to be in the numerical format, right? Correct. So whenever we will just converting the text into token, it will also get the token ID. For example, you are sitting in a classroom, or let's say you used to sit in a classroom because now you are really like professional and you do not like to sit in the classes. So let's say you used to sit in the classroom, and in your school, in your classroom, you were sharing your space with, let's say, 50 other students. And let's say we need to break down that classroom into individual student. So each student will be listed down, and that student will also get something called as roll number or roll ID, or something called as some kind of ID, right? You would be just you would have just given any kind of entrance examination, okay, JE or something, anything. So you were also given a kind of ID, right? Your roll number, something kind, some admit card ID, whatever. So actually you are the individual, but you were assigned with the number, because they do not know like who is whatever your name is, XYZ. They know you by that ID. Similarly, whenever we just break down the tokens, okay, break down the text into tokens, we know about those tokens by their IDs. And these IDs are set by the model. That's it. You cannot set it. You will understand it better when I will just showing the demo, okay? That I will be just showing you very soon. Just one more minute, because we want to talk about something called as tokenizer. Now, what is this tokenizer? Nothing. We discussed about two steps, tokenization and token ID. So when we combine these two steps and when we write an algorithm to perform both the tasks, we call it as tokenizer. Simple. Nothing complex, nothing fancy. Tokenizer is just like an application which is performing those two tasks, right? It can be a program, obviously it will be a program, computer program that performs tokenization. And this is very important, that every model, every language model has its own tokenizer, and you cannot mix match the tokenizer. Let's say you are using tokenizer from model XYZ and you are just creating or generating the data or embeddings using model ABC. No, it will not gonna work, because you will know the reason when I will just show you the demo, because you need to get the right token IDs and you cannot mix match the token IDs. Make sense? Don't worry, I will just show you. So that is why when you use different models, you often need to use their respective tokenizer. You cannot mix match it. You have to use the same tokenizer. Okay, so now let's see how does it work in real life. Let me just open one very famous tokenizer, which is OpenAI tokenizer. So I will simply say OpenAI tokenizer. It is called it has its own tokenizer. So OpenAI tokenizer, you can also search it. So this is basically the platform, okay, where you can just see like how tokens are being generated. So let's say I want to write something. Let's say let's write something. I want to ride bike, something like random text. You can also write it something. Okay, so now do you know what happened? It created 5 tokens for us. See, I has 1 token, want is another, to ride bike. Let's write something which can have more tokens. Let's say I love riding bikes and I love riding bikes and I love traveling. Okay, so these all got like 111 token. I also love pre-trained models. Okay, models like this. Okay, so now let's see. Okay, this is like a bigger text, so we will get much more relevant output. So now what happened? These are the tokens, as you can see. The first token is I, then love riding bikes, and I love traveling, and dot. See, now this dot also got now this dot also got one special token. Why? Because this dot has significance in my input. Dot highlights that this is the end of the statement, end of the sentence. So this will also get a token. See, then I also love pre and trained. See, this single word is actually broken down into two different tokens. While writing, it is just a single word. But while creating the tokens, this will get a different token, this will get a different token. Oh, then models and then dot will get a different token. That's how your input is actually being broken down in the form of tokens. And this is just for the GPT-4o and GPT-4o mini, which is a kind of more recent model of ChatGPT. If I use, let's say, ChatGPT 3.5, let's see what will happen. Currently, I have 16 tokens. If I use 3.5, it will have 16 tokens. If I use GPT-3, it has created 17 tokens. Why? Because it has like a different vocabulary. That's why I mentioned that each model has its own tokenizer. Okay, see, the difference is, I think this is a difference. It has considered this hyphen as a different token, but in the previous models, if I see, this hyphen was attached to the trained. See, this has got the same token here as well. So it depends, and you saw like model to model it varies. So let me just validate that point. If I would be using GPT-4 to create my to create basically my, let's say, tokens, okay, so I will get 16 tokens. And if I would need to just use embeddings we will just talking about very soon. So it is a kind of numerical representation. Okay, basically, let's say, converting the text into some meaning, numerical meaning. So I will not get the desired result. Why? Because this token vocabulary is different. Its own vocabulary is different. So how it can just relate with that? Okay, and this is more, you can say, this will be more relevant when I will just show you the token IDs. Let me just show you the token IDs. So this, remember the sequence. Okay, so let me just show you the token IDs. This is a token ID. What actually happened? Let me show you. See, the very first token is I. In OpenAI GPT-4o model, I is actually linked to token ID called 40. Wow. Then love. Love token is associated to token ID 3047. Riding token is associated to token ID called 29028. So what it has actually done behind the scenes, nothing fancy, just a simple mapping, and that's it. For example, let's say you have a kind of dictionary and you have mapped these things. Let's say you have written love, okay, and you have just said its value is 3047. That's it. Similar to other values as well. Let's say riding, okay, riding 29028. That's it. Why do we need to do that? It makes the life easy, right? You do not need to carry on textual data. It is directly converted into numerical. Simple. Just a mapping. Simple. So now if I switch the model, let's say 3.5, you will see values are changed. Why? Because they have a different mapping for vocabulary. So now let's say I'm using GPT-4o to create the tokens. So I want to create, let's say, meaning for love. Okay, so this model knows if I want to find the meaning of love, basically numerical meaning of love, So it needs to create the embedding for this ID 3047. Make sense? Simple. But if you provide this information that, hey, I want to find the meaning embedding, or basically numerical meaning for ID 3047 to 3.5, right? Let's say if you send this information to GPT 3.5, it will give you the meaning for different token, because maybe in its own vocabulary 3047 token is actually mapped to, let's say, hate. So instead of getting the meaning for love, you will get the meaning of hate. Are you getting my point? Are you getting my point? So that's how it works. This is all about tokenizer, which performs tokenization, breaking down the text into tokens and creating the token IDs for it. And it varies model by model. Make sense? There are other tokens as well, other tokenizers as well. One of those, I think its name was Tick Tokenizer. Yeah, Tick Tokenizer. So if you open this, it is like more of a kind of, let me just show you. So first of all, I will pick GPT 3.5 Turbo. It's fine. Okay. So now what is the system or user? You can ignore this. Simply click on cross and simply put user. That's it, because you do not need to worry about system message, user message, whatever. Okay. Simply say user, or you can even, I think, cross this as well. Let's say add message, and yeah, let's put it in the user. So let's say I want to put the same content here. Let's see how many models will we get. Simple. So now how many models did I get? 24. But you know what? There is a thing that you need to consider. So if you see this, it has actually added IM start and then user. Why it has added this? See, whenever we just want to work with the LLMs, we simply pass some special tokens along with our input tokens. IM start means you need to start from here. IM end means this particular message is end. So there are some special tokens, but you can ignore it for now. You do not need to worry about it, but it is very common sense. Whenever you just want to process your data, you pass some special tokens, which will be at the beginning of your tokens and at the end of your tokens. Make sense? And I can remove it literally. So I can just put my message here. So let's say simple. So I removed system message, user message, IM start, IM what. We are not passing those special tokens here, but you should be aware that there are some special tokens as well that we pass along with the tokens, along with the input. Okay. And we do not need to do that. Model itself does that. Sorted. So currently it has created 17 tokens for us. Very good. And as you can see that it has treated everything same. So why it has 17 tokens? Okay, traveling. I also love pre-trained models. And okay, and how many tokens did we get here? 16. Okay, so same thing. It has like one extra token, one for I love riding bikes. And see, the moment I'm hovering over this particular token, I'm also seeing highlighted token ID below. See here. So this I has the token ID 40. Ansh, Lamba, why they have same? Because in the GPT as well, we had I equals to 40. Bro, this is just a coincidence. Okay. Because for love, we have 3021. And here for love, we have 3021. What? Oh, because obviously we are using GPT 3.5. Oh man. Okay. So let's compare it with GPT 4.0. Okay. So you will see 3047. So it was just a coincidence, and 3.5 will obviously show you the same thing because we are using here 3.5 model. Okay. It should show the same thing. But if we compare it with GPT 4.0, it should have different thing, right? Good. Then riding, then bikes. So see, each token has its own token ID. So you can just try and play with it. Tick Tokenizer or OpenAI Tokenizer. It's your choice, whatever you want to use. But yeah, I just wanted to show you the process. And I hope now you are very, very clear with the process of Tokenizer. Make sense? Now you are ready to understand the embeddings. Should we start embedding? So okay, now let's try to quickly cover this topic, because we need to just go very much in deep when we will just talking about LLMs, transformers, and Encoder-Decoder part. But you need to understand this as a prerequisite. This is the fundamental thing. Okay. Embeddings. What are embeddings? Okay. Very fancy name, very fancy thing. By the way, when I was just learning about these things, I was really, really confused. Like, what are actually the embeddings? What are embeddings? So now let me just tell you everything. okay, that I also learned. Okay, so basically embeddings are nothing but vector representations of words. Wow, what a fancy statement. Vector representation of words, yes, that attempt to capture its meaning. What does it mean? For example, you have this text. Not about text, let's consider a word. Let's say you have a word called man. You need to capture its meaning, bro. Remember we discussed about this thing in the very beginning of this video, that we need to capture the meaning as well of each word or each token or word, remember? So now I want to capture the meaning of this word, bro. What is man? What is man for a word? Basically, what is the meaning of man for a computer? What is that? That meaning can be calculated using a vector. Now, what is a vector? Vector is basically, you can say, some numeric value with some direction as well. Like in which direction we are talking about. You would have studied about vectors, right? In your school. If not, bro, what are you doing? Go to school. Go back to school. So, vectors look like this. So, let's say this is the page for vectors. So, we have this particular value, x and y. X has, let's say, a value called 10. Y also has a value of 10. And if these are not vectors, if these are, let's say, normal numerical numbers, we cannot tell the direction in which direction we are saying 10. Let's say you are just running with a speed of, let's say, 10 km per hour. That's the only thing without vector. But when we talk about vector, we will also talk about in which direction you are running, bro. So similarly, see, now x and y both have similar values and both are in the same direction. So we will simply say equal vectors. Now x and y have the same value, but they are actually in the opposite direction. So we'll just call them as negative vectors. So vectors are basically nothing but when you have some value with the direction as well. That's it. Okay. This is not a mathematics class, so that's enough for you. So embeddings are vector representations of words that attempt to capture its meaning. Makes sense. So in short, we want to find the meaning of man. Exactly. Okay. So that is also fine, that we will be just finding the value as per the direction, and that will become a vector. Yes. But how we can just do that? So for that, let me just show you this practically, how we do that. So what we do, let's say this is my word. Let's say this is my word called man. Okay. And on the left hand side, I will write down my dimensions. Dimensions is basically the fancy name for features. Let's say I have here features. Okay. Features. So I will simply write some features. For example, weight, height, any other feature, let's say anything, let's say tail. Okay. Anything, bro, because these are the features which are constant for all the words. So you need to write down all the features and you will then evaluate this word man. Okay. So you'll simply write weight, height, tail, and then let's say body type, something like that. Let's say what are the dimensions, whatever. So this way you will create all the features, like not you, model will have all the features ready. Okay. And what will be the number of features? It varies model to model. OpenAI has 1536 features. 1536 features. Okay. For the smaller embedding model. Some embedding models has even less. Okay. Around 700 something. So it varies from model to model. So for example, in OpenAI, we have 1536, but in general, without OpenAI, we have, let's say, 700 plus. Okay. 700 something. Okay. So we have the feature. So we will simply assign the value of it. So we will simply say weight for man. It is like not very, very heavy. So I will simply say, let's say 0.5. Height as compared to other things, let's say 0.8. Tail, obviously no. Okay. Body type, let's say, I don't know, like it will get some score, right? So similarly, it will receive the score for all the 700 plus features, and let's say this is the score. So this score will be converted into a form of vector. It will look like this. This is a complete vector. This is a complete vector, a kind of array, you can see. Okay. This is the vector that we have created for man. Make sense? So this is the meaning of man for computer on the basis of evaluation for these 700 plus features. Make sense? Similarly, if you have more words, you can add it and you can just find the vector basically meaning for it. Make sense? Very good. So really cool, right? Really cool. We're gonna just practice this as well. Don't worry. This is really cool. But embeddings were very, very popular, obviously, in the year 2013, and it is actually evolved very, very, very much with the course of time. And obviously in the world of LLMs, it is evolved to the next level. Let me just tell you what I do. What do I mean? But before that, I hope now you know what is the meaning of embedding in a nutshell. Nothing but just the vector representation of the word. That is it. And what will be the size of it? It will be purely based on the number of features, number of dimensions we have. If we have 700 dimensions, the size of this array will be 700. If we have 1536, the size will be 1536. Nothing fancy. Okay, makes sense. So now let me just tell you about the types of embedding. There are basically two types of embedding, static and contextual. So the embedding that we have made for man in just previous slide, what type of embedding was it? Just a guess. Tell me. So that embedding was just a static embedding. Was what? Static embedding, right? Why static? Bro, I just took a word man. Okay. I just took a word man and I evaluated the word man among all the features. If I give input, let's say I call I am a man, okay, or anything related to man. So the meaning, the vector for man will be the same. Makes sense. A very good example of this is, which is written in so many books as well. So let's say the meaning of bank. Meaning of bank. So now if I want to find the meaning vector for bank, okay, or let's say any word which has like multiple meanings. Very good example. Bank is the perfect example, and I also read the example for bank when I was just studying. So let me just show you. So let's say I am trying to find the meaning for bank in this text. I want to go to the river bank. Okay. I want to go to the bank or any bank. Let's say XYZ bank. Okay. Bank for anything. Let's say for account opening or for anything, for ABC task. Okay. And this task is actually something called as for something related to banking. Okay. You can just say anything, literally anything. So now just tell me one thing. If I want to find the meaning of this bank word, okay, it will get the vector as we know. And now if I want to find the meaning of this bank, I will get the same vector, right? Because the word is same, the features are same, so vector will be same. But just tell me one thing, is this bank equivalent to this bank? Obviously no. This is like a river bank where you can just sit and just have some fun. This bank is actually the financial organization. Makes sense? So both banks are different, but the word is same. Ansh, Lamba, you are absolutely right. So how we can just solve this problem? This problem is actually solved using contextual embeddings. And that's where the concept of LLMs come to the picture, basically transformers. Transformers solve this problem. How? Obviously, we are just learning everything step by step. But for now, you can say contextual embeddings are created by transformers. So what do we mean? We mean to say that even if we have the same word, that meaning, like the meaning of that word will be influenced by the other words in the sentence. For example, what will happen? So first step will be the same. So let's say you just wrote both the sentences. I want to go to the river bank, and you wrote I want to go to the XYZ bank for ABC task. Okay, or let's say to see the manager, whatever. So now do you know what will happen? Let's say we want to find the embedding, basically meaning for this bank word. Okay, so what will happen? Yes, it will create the same embedding like this, having all these 700 plus features evaluated. Okay, so it will simply write 0.8 whatever, 0.1 and 0.6 whatever. Okay, so it will write all the 700 plus features. This is the first step. Yes, and you know what will happen? Then this vector, this is a bank vector, by the way. Let me just write it for you. This is a bank vector. This bank vector will be changed and modified. Why? Because this particular token, this token will be giving some context. This token will be giving some context. Similarly, all the other tokens will give some context, and finally this will be the biggest context decision maker, obviously. So this will also provide some context, and this particular static embedding will be changed into contextual embedding. You are absolutely right. Make sense? So this will be changed and modified like this. So let's say this value is now 0.2, 0.4, 0.9 and blah blah. Okay, makes sense? So what we want to say in a nutshell, we will simply add some context. So what we will do, we will say, hey, I want to add I. We want to add want. We want to add to, go, to, river. And obviously, each particular word is contributing towards the meaning of bank, right? Because here the biggest contributor is word river, or basically token river. So how it decides like which token it should prioritize the most, how it can just do all of these things, you are learning that thing. Don't worry about that as well. We will be just covering that as well. So now we will simply say, hey, add 10% of this context, 5% of this, 10% of this, and then 80%. Let's say I'm not calculating all the percentage. Let's say 80% of the token context from this token alone, because this is a decision maker. So you have added 80% of the context from this river embedding, and you have added that thing into this particular vector. And then it has become contextual embedding because it has a context. Got it? So similarly, this bank embedding will also get this thing, initially, but it will have its own contextual embedding based on these tokens. XYZ bank, because it has the bank name as well, and ABC task, maybe any financial task. So those things will be contributing towards making it contextual embedding. Make sense? That is the concept of embeddings. Make sense? Okay, very good. So this is all about the embeddings, static and contextual embeddings. Make sense? Very, very, very good. Now I want to show you the code as well for that, so that you can also practice and you can be aligned with the approach, like how we can just do all of these things. Okay. So for the coding part, what I will do, I will simply open a very good platform for that, which is free of cost and which will make your life very, very easy if you want to try something with the LLMs and all. So it is called Google Colab. Okay. So just search Google Colab and just click here, and what it will do, it will simply open your Google Colab workspace. What is this Google Colab? Google Colab basically is the platform which is provided by Google, and if you have used Jupyter Notebook ever in your life, This is the same thing, but it is hosted on Google server. So whenever we create this Google Colab notebook and when we connect it, see there's a button called connect. When we say connect, so what it will do, it will create this notebook. Let me just create a new one, by the way, because this is the default Colab notebook. So I'll simply say file and new notebook in Drive. So what it will do, it will create a new notebook in your Google Drive. Okay, whatever account you have linked to this. And this notebook, let me just click on connect first so that you can see. So it is now saying connecting. So now what it will do, it will not run this notebook on my machine, because Jupyter notebook runs on your machine, on your RAM. And if you just want to use LLMs, they are very, very huge in size. They would sometime require GPUs, and obviously not everyone has GPUs in their laptops, graphic cards and all. But obviously we want to learn, so this is the best platform for it. And don't worry, I'll just provide this notebook as well in my GitHub repo. And for that, let me just rename it. So let's say embeddings. Make sense? Okay, good. So now we'll be just covering embeddings. Okay. And this particular notebook will be running in the Google server, not on your machine. You will say, Ansh, Lamba, where is the Google server? Okay. Just click here on this button in this folder. Okay, and just wait for a few seconds. You will see everything here, CPU, storage, whatever storage, because by default you get, I think, see 69.5 gigs of space. Okay, and you can use it anytime for free of cost. Wow. And you can even install any model, any large model, and it will not install on your machine. It will be installed on this machine, see. So Ansh Lamba, let's say this session is signed out. Maybe you are, let's say, using the same notebook second day. What will happen? Very good question. If you are using this notebook for the second day, when your session is like obviously terminated, then you have to reinstall the model, because that particular server will be lost. Because this server, this virtual machine will be there just for that particular moment. The moment you timed out the session, it will be lost. So you have to download the model again. But it's not a big deal. You just need to write one single command and that's it. And you are just getting it for free of course. So I don't know what's the pain point here. Okay. So now let me just show you the code for the embeddings. And you would also need to install some things. And first of all, we can install this transformer. Okay. And I will simply say install this. So simply write this command and simply hit shift enter to run this command. Okay, and let's wait for it to download, and it will take some time obviously because it is a big model and it is downloaded very, very good. So now what we need to do, you can also go to runtime. Okay, and if you go to runtime, you will see change runtime type. So currently by default it runs on CPU. Okay, but if you want to use something big, then you have to switch it to T4 GPU. If you switch it to that, so what it will do, it will create a new runtime for you and you can use the GPUs, and GPUs are required if you just want to run the transformers. Okay, so it is now connecting it, and now you will see my disk space is also bigger and my runtime is connected to T4 GPUs, which are required. Okay, so let me just write the code for that. So first of all, we need to import the models. Okay, so there are basically, let's try to find the embedding for each token first of all. So let me just write, oh man, yeah. So here, let me just add a markdown. So I'll say token level embedding. Okay, so I'll simply say from transformers, because we have just downloaded or installed transformers. From transformers, import auto tokenizer, auto model, or I can just copy the code. Perfect. So if I just run this code, let's see what will happen. First of all, it will create the tokens for me. Remember the first step, the very first step is creating the tokens, and we are using the same tokenizer to create the token for the same model. Okay, it will take some time and let's wait for it to just create the tokens. and it will just download all those things, configuring JSON and all. Make sure your runtime is running on the GPUs, not on CPUs. And I've just shown you like how you can just change the runtime. Okay, so just make sure that runtime is on GPU. Sometimes it can throw error if you're just running it on CPU. Make sense? Because it needs to install so many things. So currently we have just got the tokens. Let me just write it tokens here as well to see the tokens. So see, it has created tokens for me 1 3 1 4 1 4, and now you know what are these things. These are token IDs, right? Very good. So 1 3 1 4 1 4 2 3 2 6 1 2 7 7 6 6 1 6 6 6 0 1 1 9 3 2. So these are basically the tokens, right? Now I want to find the contextual embedding, not just static embedding for these, contextual embedding for this. So I will simply write this code and let's run this and let's see what do I have got. Contextual embeddings. So now this is the contextual embedding. Wow. Obviously, like this is very not very readable, but this is a vector. And how many vectors do I have? Obviously the number of tokens, the number of vectors. Simple. Okay, and if we just want to see the size, okay, so we can simply say embeddings dot shape, and you will see 10 into 384. Why 10 into 384? Why? Very simple, because we have 10 tokens. See, 1 2 3 4 5 6 7 8 9 10. And what is this 384? These are the dimensions, these are the features. Remember I mentioned that it can be 300, it can be 700 plus, it can be 1536. In OpenAI embeddings we get 1536. Wow. Yes. So this is all about finding the contextual embedding for each token. For each token. Okay. So we have 10 different embeddings. But do you know what? Remember that I just mentioned that we will be using Encoder-Only transformer to create the embeddings. Remember? So let's say I want to create only one single embedding for this entire text, because I don't want to just create individual embedding for each thing, because I want to use Encoder-Only transformer. Okay, so in that particular scenario, you have to use sentence level or paragraph level embedding. So what it does, it aggregates all the vectors and creates only one single embedding for the entire input. And that embedding will have the context of the whole sentence instead of single word, the whole sentence. Simple, nothing special, nothing complex, just embedding of the whole sentence. And how it does that, it simply aggregates all of the embeddings. That's it. So let me just write the code for that as well. So now it is called sentence level transformations. So let me just write the text first of all. Sentence level embeddings. Okay. So same thing. Okay. So let me just run this. And it will take some time because it will download something. I think so. Yeah. So see, all of these big models are not downloading on your machine. They are being downloaded on server. So let's see the embeddings now. So this is the embedding. Wow. This is the full embedding. And let's see the embedding shape. 768. Why? Because this model has 768 dimensions. So what it has done, obviously it first created 768 dimensions vector for each token, and then it aggregated and just created only one embedding vector. So this is just, see, only one embedding vector of 768 values. That's it. See, just one array. So that means this whole sentence is now represented as only and only one embedding vector. Only and only one embedding vector, whatever value we have, blah, 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 blah. Only and only one embedding vector. But you know the process. It will not directly create the embedding for whole sentence. Obviously, it created the embedding for each token first of all, and then it aggregated all of those things. And in order to do that, it used something called as Encoder-Only Transformer. Okay. and you will see the architecture as well, don't need to worry. But you first need to understand like what is it doing before understanding how it is doing. Exactly, you first need to understand what is it doing before understanding how is it doing. Because if you will directly jump on, hey, how encoder only works, hey, how transformer works, without even understanding what is it actually doing, you will not be able to understand. Then you will be just learning for the sake of learning. Hey, I just want to learn how it works. But why you need to learn? What is it actually doing? It is doing this thing. Make sense? So now you have a very strong conceptual knowledge, fundamental knowledge for embeddings and tokenization. So let me just take you to the architecture part, because now you are ready to understand that thing. Okay, because now you have very rich understanding of embeddings and all those things. Okay, so let me just show you first of all the example, and I will just provide this notebook. Okay, let me just download it so that I will not forget. Download. Okay, so I will just provide this. If you want to use it, how you can just use that, go to file and go to open notebook and upload my notebook that I'll just provide in my GitHub repo. Simple. Or you can just copy paste the code as well here. Simple. And just keep it as your notes. It will be really, really handy. Okay, very good. So now let's actually try to see what are transformers. Forget about decoder only, forget about encoder only, forget about encoder decoder both. We first need to talk about ChatGPT. Why? Because this is the model, this is a transformer you are using on a daily basis. Okay, if I open ChatGPT. Okay, now the very first initial concept of transformers was actually a combined form of encoder and decoder. And I have already mentioned this thing in the beginning of this video, that ChatGPT uses only and only decoder-only transformer. Make sense? Decoder only. Now, this is a very, very good thing, and this will be a game changer for you. Instead of understanding encoder, decoder both, you first need to understand decoder-only transformer, because this is the GPT model that we are using currently in almost all the solutions. When you understand decoder only transformer, then you can understand the encoder only and encoder decoder. Really? Yes. If you will directly jump on to understand encoder and decoder, you will be confused. This is my personal experience as well. So just try to understand transformers from the decoder only perspective. Obviously it has like numerous benefits, plus the biggest benefit is you are already using ChatGPT on a daily basis, so you can really feel relevant. Okay, so let's start decoder only transformer with this small example. Okay, so what is happening under the hood when I write something? So let's say I write a beautiful, not beautiful, write a lovely message to my friend. Why? I don't want to let's say write a good quote for today. Okay, I'm simply writing this, and let me just hit enter. So what it did, here is a fresh quote for today. Let today be the day you choose progress over perfection and intention over impulse. Nice. So now what happened? You wrote something, you got the answer, and you are satisfied, right? But how it actually did this? How? Do you know how? Let me just tell you. So let's take an example of LLM, because obviously this is using LLM under the hood. ChatGPT is just like the web user interface, but under the hood, it's just like LLM. So what is happening? Let's say this is you. Okay. And whatever your name is. Okay, so let's say this is you, and you are talking to this LLM. Okay, you are talking to this LLM. Let's say like this. Okay, so now what happened? You provided some input to this LLM, that write a quote. Okay, you provided some input. Okay, this thing like write a good quote, whatever. So you said write a good quote for today. Okay, you provide this input. LLM processed it and it generated this text. Let today be the day you choose progress and whatever. Okay, let's say this is the text it returned. You are seeing it from this perspective. Obviously, this is your input and this is the output you got. So you are actually seeing it from this perspective. But that's not how LLM works. What do you mean? It didn't generate this particular output in one go. Okay. So what actually happened? So let me just tell you what actually happened. This output that you are seeing that is just generated in within few seconds and you are seeing wow is not actually one step thing. It has actually gone through so many iterations. So what actually happened? So when you provided this input, LLM just predicted the next word called let. That is it. That is it. Because what is LLM? What is LLM? We discussed it, right? LLM is just a language model. And what is a language model? Predicting the next word only. So based on this input, it predicted this let, and that is it. This is iteration 1. This is iteration 1. Okay. This is iteration 1. This is iteration 1. Now what will happen? This let will be appended to the input. So now what it will become? It will become like this. Write a good quote for today. Okay, and then it will have let as well. Now this will generate second token. It will predict second token. And what will be the token? The token will be today. That is it. That is it. This is iteration number 2. Wow. This is iteration number 2. So it is actually doing the iterations for you. Every time it is just predicting the next word, and whatever it predicts, it appends that output into your input and it passes that same input along with that generated output to predict the next token. So it is just doing this thing. LLM is just all about this thing. But what is so magical in that? So obviously the question arises how it is able to predict let, how it is able to predict today. That is all the magic that is happening within this LLM. Okay, exactly. And within this LLM, so many processes are being processed. Really? Yes. Make sense? So that is how it is working under the hood. It is predicting let, it is predicting today, and blah, 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 blah. So all the token will be appended like this. See, let, and then here, then today, and then so on, then so on, then so on, then so on. So it is predicting just the next word. Okay. And it uses all of those things that you are aware of now. Tokenization, tokenizer, token IDs, all of those things. Now embeddings. Now we just need to assemble those knowledge. Now you have the knowledge. Now it's time to assemble all of those knowledge step by step, just to see how it works. And obviously along with some special processes that it performs under the hood. Okay, make sense? And remember, we are covering decoder-only transformers. Make sense? Okay. So now let's see the processing step by step. Okay, let's see. So let's start with our decoder-only transformer, because now it's high time to talk about it. Okay. So now what are we gonna do? We're gonna understand the entire process in detail. So it will be technical, yes, but you are prepared for it. Very good thing. It will have the real example, like how things actually get processed, and you are ready for it because now you have very strong understanding about embeddings, tokenization, and blah, blah, blah. That's why I covered those things first, because you need to have that knowledge, right? Very good. So now what you can do, you can literally take out your notebook, because this particular section of the video is like very technical, and just good advice from this guy. You would need to watch this particular section of this video maybe multiple times. Let me share my personal experience. Okay, when I was just learning about transformers, I literally watched or basically read, and you can just create a blend of all these things like read, because they were like not a best guide. Okay, so I went through at least 8 to 10 times. Yes, and I'm not exaggerating, 8 to 10 times to understand this concept. So if you do not understand this transformers decoder only architecture in one go, that is fine, because it is very new to you. You are not someone who has developed this thing, so it is very new to you, and your brain would need some time to understand and absorb the knowledge. So I would need a small promise that you would watch this particular section, only this section, only decoder only transformer section of the video. Okay, and I'm not just saying it for the sake of views. Please trust me. I'm just saying this for your sake, for your information, for your knowledge, and choice is yours. Okay, so if you watch this video, like this section of the video multiple times, it will be helping you a lot to understand the concept. I will try my best to make things easy, I promise. But I would need a promise from you that you would at least, let's say you understood everything in one go, and I will take care of it. Let's say you have understood everything in one go. Still watch this video, this section of the video one more time, so that you can just revise those concepts. Make sense? Okay, let's get started. So first of all, let's start with a real-time example. Let me just open my LLM. Okay, not my LLM, like ChatGPT LLM or very popular LLM. So let's say I want to say something like this: the white cat sat on the, because this is one of the popular examples you would read everywhere in the research papers, not in the research papers, basically in the blogs, in the very popular articles. So that is why I thought of just keeping the same example, so that whenever you will be just reading any article, any blog in future, you will feel relevant. Okay, so let me just take this example. I have just modified this a little bit. I have added white. Okay, so you will understand like how things are going, and this particular change will help you a lot in understanding this thing. Okay, so let's say I just wrote this thing, and let me just hit enter. What will happen? It will simply say, how would you like to finish the sentence? Here are a few options: window shell, soft cushion, garden wall, keyboard, whatever. So let's look at this with another lens. So we have confirmed this thing that LLM will just predict the next word. Let's say I am building an LLM, or let's say I want to use an LLM to predict the next word for my email, right? We discussed that example. I want to see what will be recommended after this. The white cat sat on the. So if I just submit this request to LLM, obviously it will give me more than one option, because it is a kind of it is generating the text for me. So it will just push me all of those things. But let's say I'm just building this LLM for my email recommender system, not email recommender, real email recommender. Let's say I am just implementing this LLM in my current email application, which can just suggest the users the very next word. Make sense? Because that's what it will do. It will simply say the white cat sat on the something, and then it will keep on adding those text, and will do those things. So let me just modify this prompt a little bit. I will simply say complete the sentence, because I need to just provide this information in the prompt. Complete the sentence and keep on writing at least 2 lines. The white cat sat on the, that's it, because that's what it will do under the hood. So what it did, the white cat sat on the windows well, watching the golden morning light, blah, 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 blah. So it generated this text for me. How? Token by token. And you know how it does that. It keeps on predicting the next word, and it will keep on appending that token into the input, and it will keep on repeating this thing, right? You know this. Very good. Now let's take the same example, and now we need to understand how it is doing this, right? That's the purpose. We need to understand this. Okay, so let me just keep aside this example, and let's take the example further to our slides. So for example, if we just want to talk about this thing, technical point of view. So this is our example. The white cat sat on the, and our end goal is to predict the next word. Yes, you are very well aware about static embeddings, contextual embeddings, because we're going to use those things here. Okay. And if not, you can just revisit the part of this video where we just talked about static embedding and contextual embedding. Make sense? Very good. Now just tell me one thing. If I ask you to predict this word, let's say you are an LLM, you want to predict the next word, how you will just do that? You will simply say, I can predict, let's say, on the sofa. Okay. How did you do that? I just read the sentence and I predicted this word, sofa. Okay. 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 Makes sense. But did you use, because you are an LLM, did you use contextual embedding or static embeddings? Because obviously you have the meanings for the, you have meanings for white, you have meanings for cat, and so on. Did you use static embeddings or contextual embeddings? Bro, obviously contextual embeddings, because I need to know the context. Let's say I want to first of all know who is going to sit on something. It is cat. Okay. First context. Second context. What color of cat it has? Like what are the features for that cat? Okay, white cat. Okay, so is it going to sit or is it going to, let's say, relax on sofa or whatever? Third context. So in short, you are using contextual embeddings, right? Contextual embeddings, but our system is only capable to build the static embeddings. So transformer will do that thing. Decoder-only transformer will do that thing for you. How you can just bring the context. For example, you want to bring the context for this particular thing. So you need to know, hey bro, how this cat will bring the embedding from this thing as well, because white is contributing to this particular embedding, sat is contributing to this particular embedding, and so on. Like everyone is contributing to this particular thing, right? Yes. That's where the role of transformer comes into the picture. Okay, so let's see what is the first step that will happen if we just provide this input. The first step is very, very simple. It's called tokenizer. Oh, we already know about tokenizer. That's why I discussed it before. So first thing will be like this. It will convert your input into tokens. So let's say this is one token, this is second token, this is third token, this is fourth token, this is fifth, and this is sixth. Make sense? So this is step number one, breaking down the text into tokens. Make sense? And then it can just assign some IDs. Let's say this is 42, this is 110, this is, let's say, 39, 12567, and so on. Now you know the things, right? Okay, good. So tokens are created and token IDs are created. This is step number one. Okay. And all of these things that we are just going to discuss in this particular section, all are step by step. Okay, good. So tokenizer is done. Now what's next? The next thing is static embeddings. And you are already aware of this thing. So what we do, we simply create the static embedding of each token, or you can say for each token ID, because same thing, token or token ID, just a mapping. So just for the sake of understanding, we are simply keeping it as a token. But you know that each token is aligned or mapped with the token ID. Static embedding. Static embedding doesn't have any kind of context. These are static. White will be white for everything. It doesn't know like, is white a cat? Is white a wall? Is white bike? White car? Nothing. White is white. It doesn't care about anything. Simple. Okay, static embeddings are also done for each token. Make sense? Very good. Now, one more thing, which is very, very important. If you can just find it right now, like after creating tokens and everything, what is that particular thing, which is very important, which can influence the context to high level? What is that thing? Just think about it within the sentence, and it is very obvious. Okay, time is up. Let me just tell you what is that. It is called positional encoding. In layman terms, position of each token. If I say the white cat sat on the, or let's say the predicted word is sofa. Let's say this. The white cat sat on the sofa. This has a different meaning. If I say the white sofa sat on the cat, same tokens, same words, same embedding, but context totally changed just because of the position of one token was replaced. Make sense? I said this is basically the input and each has its own embedding, okay? And we want to find the context, obviously, but in order to find the context, position is very important of each token. Because I said, what if the sentence look like this? Let's say the sentence look like this. The white sofa sat on the cat. This is totally different, bro. This context is totally different, but same tokens. So position is very, very important. So position encoding is nothing but just providing the position of each token. Just for the simpler understanding, you can say 0, which is the index, 1, 2, 3, 4, 5. So when these things will be going to the transformer, because these are the prerequisites for the transformers, when it will be going to the transformers, it would know that this embedding for the, or let's say embedding for white, is actually coming at the 1th position. Make sense? Very, very common thing. Okay, very good. Now what will happen? Now magic will happen, and because we need to now set our goals. So now what do we have so far? We have this input, the cat sat on the sofa or whatever, because sofa will be predicted, but we have this input. So these are the static embeddings, right? These are the static embeddings with positions. Okay, static embeddings with positions. Make sense? Now our end goal is we want to convert these static embeddings into the contextual rich embeddings. Make sense? What do I mean? When I say cat, so now cat's embedding is E3, basically embedding 3. Okay, cat's embedding is E3, or you can say embedding 3. I want to add the context to this cat from this token as well, because white cat makes the difference, bro. If we just say cat, it is not actually providing any type of context. The is not actually contributing a lot, but still it needs to have the context as well of this token. Then sat, because what cat is going to do? Sat on, and then the is not contributing, but it will contribute a little. Make sense? Very good. So now when cat embedding will have the context from all the other tokens, it will become E3 dash. That means now E3 is not just a static embedding, is not just like the same meaning or same cat embedding for everything. No, it has the customized or contextual embeddings. It has the context of the near or neighbor tokens. Understood? Simple. Okay, very good. And how it will be done? It will be done using this particular architecture. So what happens, whatever text we are just passing it here, like input text, will go through all the steps that we have just discussed. Tokenizer, then static embedding, okay, then position encoding. Everything will be done here in the input text, and at the end of that particular thing we will get static embeddings, right? E1, E2, E3. So these are the static embeddings. Make sense? Okay. Static embeddings. Make sense? Now this information will go to something called as transformer block stack. What is this? We'll be just talking about that. Transformer block stack. By the way, this whole architecture is called transformer, but within transformer we have transformer block stack. So do not feel like, hey, only this part is the transformer part. No, no, no. The whole architecture is for the transformer, but this is the inner part of transformer, which is called transformer block. Make sense? Very good. So it will do some magic, and it will convert this static embeddings into the contextual embeddings. E dash. Okay. And what is this LM head? LM head is just the predictor. Based on this contextual embedding, it will predict the very next token. It can be sofa, it can be mat, and it can be anything. Chair, anything. Table. So LM head work is just to predict the next token based on the contextual embedding. But the heavy lifting is being done inside this transformer block. Again, transformer is the complete architecture. This is the transformer block inner part of transformer. So do not be confused, okay? Because it is confusing, same name. But yeah, transformer block is the inner part of transformer. But the whole thing when combined, it is called transformer. Make sense? So now we need to see step-by-step process what actually happens inside this transformer block. Now we need to go inside this transformer block, like what is actually happening, right? Okay, so how we can just do that? Let me just show you. Let's first of all talk about the transformer block stack. Okay, and just a quick tip. Before understanding all the transformer block stacks together, you first need to pick one and you need to understand what's going on inside it, because the same stuff is going on in all the other block stacks as well. And what is the difference, you will get to know after this. But let's pick this one block, okay, and let's see what is happening inside this, because the same stuff, same process is going on in the other transformer block stacks as well. Okay, so let's pick one and let's see what is going on. So inside this one transformer block, we have three main, I would say, pillars for the contextual embeddings. And this process is called as self-attention. Okay. Three pillars: query, key, value. Query, key, value. You just need to understand these three things. And obviously it is not very easy, but I will try my best to make you understand this thing very easily. So query, key, value. These three pillars make sure that you are converting your normal static embedding and you are getting richer contextual embedding so that LLM can generate and predict the next word better. Okay, are you ready to understand these three things? It will be fun. Okay, first of all, these are a kind of variables. Okay, simple variables. What they are doing, how they are being calculated, hold on, let's see it one by one. So now, in order to find the self-attention, now what is the self-attention? It is just a fancy name for the same thing that we have discussed for contextual embedding. So for example, we need to discuss about the cat sat on the, okay. So now let's say you want to find the embedding for, oh, we have the white cat. Be specific, Ansh. The white cat sat on the, perfect. So we just want to, let's say, find the embedding for cat, okay, or like anything. Just for now, let's say cat. So we need to attend all the other tokens. So let's say we need to attend this token. We need to attend this token, or basically other tokens will be attending to this, vice versa, whatever way you want to pick for understanding. So this will attend to this particular thing, the sat, and then on, then the. Similarly with other tokens as well, for the other tokens will be attending to that, then white, then cat, then sat, then on, then the. This way other tokens will be just putting some attention to the one token. It is called self-attention. It is called what? Self-attention. Make sense? Just a fancy name, just a technical name for the same thing that we have discussed. Okay, very good. But yes, you need to be aware of these technical terms. That's why I've written self-attention. Now what happens with these query key value pairs? It is very easy. So first of all, we will create our static embeddings, and we have already created that. Make sense? Nothing is wrong with that. Okay, so E1, E2, E3, E4, E5, E6. Very good. Now when these will be going under the self-attention process, so this thing will be started with query. What do I mean? So for example, just tell me one thing. If I want to find the contextual embedding for cat, my query will become what? cat. My query will become cat, right? So what is a query in a nutshell? Query is just the token for which we are trying to find the context. And it will be changing, or it will not be changing, by the way, it will be calculated for all the tokens. So obviously if we want to find the contextual embedding for the is the query. And if we just want to find the contextual embedding for white is the query. If we want to find the contextual embedding for cat is the query. Okay, so query is nothing but the token for which we are trying to find the contextual embedding. Simple, sorted. Okay, do not make it complex. It is written there, something else is written there, nothing. Just focus here. So token for which we are just trying to find the contextual embedding will become our query. Simple, sorted. Okay, very good. Simple. Query is done. So let's see how our query will look like. So our query will look like this. Whoa, what just happened? Wait. Nothing happened. Hold on. So let me just tell you. Now I said, let's say we want to take an example of cat. Okay, cat is a query. We know that. But we need to convert it into something called as query vector. What did I say? Query vector. Very good. We need to convert it into a query vector. Why? Because we already have an embedding. Yeah. So what we do in order to convert it into a query vector, we have something called as weights. And you do not need to do anything for this thing. Okay, it is totally subject to the model or LLM that you are using. Okay, so what we do, we simply multiply these weights to our embedding to create the query vector for that particular query. So in short, you can say that we had the static embeddings, okay, and we added some weights. Now what is this thing? What kind of weight? See, this is a query, right? So we need to add some weights so that it can ask the relevant question to the neighbor tokens. Hey, do you have any kind of adjective? Hey, do you have any kind of some features? Hey, so those questions like features will be added through these weights. Oh, so this will actually add the questioning power, because this is a query, right? So you are adding some weights so that this normal static embedding will become a query vector. Okay, just a query vector. That's it. Makes sense. So query vector will be ready, and how it will be ready? Static embedding multiply with weights, and this will be constant. Okay, this will be constant. Okay, for one transformer block, it will be constant, like normal, not for transformer block, like one transformer block. Yeah, one transformer block. So it will be constant. Make sense? Okay, very good. Now our query is done. So we know that every token is a query. Okay, very good. Now I want to ask you a simple question. Okay, what's that? The second variable is key. Okay, now what is key? Just think about it. It's very obvious now. So let's say I want to find the contextual embedding for cat. Cat is my query. So all of the tokens which are adding context to that particular token, which is query, are called keys. So let's say I am finding the contextual embedding for cat. So who all are contributing to that particular token? Obviously all. Da is also contributing, white is contributing, sat is contributing, on is contributing, da is contributing. So all these are my keys. Oh, yes, simple. All these are my keys. So in short, all the tokens are queries, all the tokens are keys, but with respect to that particular token. Make sense? Make sense? Very good. Very good. So now let's see how we can just calculate the key vector, very similar to query vector. So first of all, let's quickly complete this query vector. So you know now like this E1 will become Q1, E2 will become Q2, E3 will become Q3. It's very obvious, like we do not need to explain it further. because we know that each embedding of query will become Q1. Okay. And now we are actually talking about key vector. So key vector will be very, very similar to that particular query vector. That means normal static embedding multiply with some weights. So for example, let's say we are finding the contextual embedding for cat, and white is one of the major keys, right? So what we will do, we'll simply multiply the static embedding for white, which is a key, with some weights. Again, what are these weights? See, now we need to add some weights which can just tell more about them. For example, token is white. So this weight will tell, hey, I am white. Hey, I am an adjective. Hey, I am this, I am that. So this weight will make sure that keys are able to express their qualities, express their features. So this weight is responsible for that particular purpose. Make sense? Make sense? Simple. Weights are just providing some more power to the static embeddings, because static embeddings are not very, very useful. Okay. So we are simply adding some power, some special touch. That's it. And what will happen? Each embedding vector will be converted into K1, K2, K3, K4, K5, K6. Simple, because each token is a query to the other token. Makes sense. Okay. So now what we need to do? We have Q vector, we have K vector. We have Q vector and we have K vector. Okay. Now we need to find the relevancy score. What do I mean by that? So let me just bring the screen. So for example, I wrote the white cat sat on the. If I want to talk about specifically for cat, just be honest. Just be honest. Are all the tokens relevant or equally relevant to cat? Or for this particular input are equally relevant? The answer is no. White is more relevant than the. Sat is more relevant than on or maybe the. So we know that all the other tokens are actually attending or adding context, but all of those tokens are not like adding the same context. We need more context of this token, which is called white. We need less context for the. We need more context on sat, because these are the major contributing factor. Makes sense. Makes sense. Because you need to know like what are those tokens which are actually contributing more for your output. Here, even you can say any kid will understand that in order to predict the next word, two major contributors are white, cat and sat, like three major contributors. But how do we know? We know this by calculating the relevancy score. So what we do, we simply create a, you can say cross multiplication chart. Let me just show you. So it will look like this, relevancy score. So this is Q1, that means query of 1, which is the, query of 2, which is white, query of 3, which is cat. So let's say we want to find the relevancy score of white with respect to all the other keys. With respect to what? All the other keys. Okay. So this Q3, which is cat. With respect to the, it is 91%. Obviously these are like arbitrary numbers. Okay. Just to explain you the things, but it is not very, very relevant. I just put 91, but for the sake of understanding, you can say simply 1, not very contributing. Okay. Then white. White is actually, this key is white. Okay. This is the, this is cat, this is sat, this is on, this is the. So this cat will attend, this cat query will attend to all of the keys, and this multiplication, this is basically the dot product. Okay, dot product of Q and V. Make sense? This will be the dot product between this vector and this vector. Q3 and K1, then Q3 and K2, then Q3 and K3, then Q3 and K4, then Q3 and Q5, then Q3 and K6. Wow, literally wow. So here, if I write the white cat sat on the, so this is now the query, this token, and it is actually, this is the query, okay? This is the query, and now these are all the other keys. This is a key, this is a key, this is a key, and this is a key, this is a key. So it is actually applying the dot product with each vector to find which token is more relevant. Higher the production, basically higher the dot product value, higher the relevancy score. So maybe this Q value, this Q query will get more value for this white because it is more relevant to this. This Q vector will get more value for SAT because it is more relevant to this. So this will tell us the relevancy score. Okay, so far so good, very good. So we have found the relevancy score, which is the backbone of everything, and that's it. You will say, Ansh Lamba, it is that simple? Yeah, just few steps are left, but this is the backbone. That's it. This is the most confusing part, which is now very, very simple. And yes, you can just thank me in the comment section, and you can hit the subscribe button if you just love this explanation. Okay, so now we know that we have the relevancy score. Okay, now this score is like not looking very, very good because some number is 98, some number are minus 21. So we need to basically normalize these numbers. So for that, we use a technique called softmax, or basically you can say before that, yeah, before that, we use something called as, let's say, softmax to do that. Yeah. So what it will do, it will simply convert your bigger numbers into a kind of distributed, normally distributed numbers, which are not very, very big, because we can simply find the probability of it, which can just contribute to 1. Okay, 0.2, 0.81, 0.1, 0.91. So we are just trying to diverge the numbers, because currently the numbers were like so big, 98 minus 21. So this is just a way to better represent the numbers. That's it. It is doing nothing else. Softmax is a technique to convert your bigger numbers, like distributed like a mess. It will simply convert it into a probability that, hey, this Q3 is more relevant to K2, which is white. Oh, and the probability for this, or basically you can say relevancy score for this, is 0.9. So more it is closer to 1, more relevant it is. It is the simple thing. And do you know what? It is very, very, very handy when we just want to calculate the final step. So I personally love this softmax, but it is a kind of just to convert those big numbers into easy to understand numbers. Simple, nothing else. Do not be confused. It is a special step in NLP. Hey, it is something else. No, nothing else. Now, I want to talk about a very, very special thing, which is called masking. So before creating or before finding the softmax, before reaching to this step, we need to include one more step in our table. What is that step? Let me just tell you. So that step is called masking. Woo. Wait, just look at the table. You will see something. Okay, we saw it. What? We saw Ansh Lamba minus infinity. Do you know why you are seeing minus infinity? Do you know? Do you want to know? Let me just tell you. So this is the major step in your decoder-only transformer, and this is the differentiator between decoder only and encoder only. Obviously we are not discussing encoder only, but I'm just informing you. So when we just find self attention, after finding the self attention, we also mask it. Why and what exactly we are doing? So let me just tell you what is our example. Our example is the cat sat on the, or the white cat sat on the. Okay, makes sense. Do you know what? In decoder only transformer, we perform masking. That means, let's say this is the query. right? This is the query, cat. In self-attention, we got to know that this token will contribute on 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 this, and this token will contribute on this. But you know what? We will mask all the future tokens. That means these tokens are not visible to token cat. These are not visible. Only this token and this token is visible. So it will only attend this token and this token. And why do we do that? Because decoder only model is designed to predict the next word. So it generates the next word. So we have to mask the every next token so that it can generate it on its own. Oh, okay. So when we say we want to find the contextual embedding for cat in decoder only architecture, we are simply saying this cat will get the context for sure, but only for the previous tokens, not from the next tokens. Understood? Yes. And why do we do that? You also know the answer. Yes. Now the question is, how do we mask it? So what we do, we simply provide a very low value to our key value, key pair, basically not key value, just key. Okay. Just key vector, very, very small value like minus infinity. Because what will happen? This value is so small. So it will eventually return 0 when you will be just soft masking it. Like soft maxing it. So when we apply the process of soft max, this minus infinity will be converted into 0 because this is like very small value. That means we can simply ignore this value. This is not even like relevant to our dot product. That's what we want. That's what we want, because we want our token or basically query to only and only attend the previous tokens, and that's it. Oh, so the moment we assign minus infinity here, so this after softmax, okay, so currently it is not softmaxed. So when we just apply softmax, these numbers will become 0. See, this shows that only query is attending to K1 and K2. Query 4 is attending K1, K2, K3. Query 5 is attending this, and query 6 is attending all the other tokens. Query 6 because it is the last token. And by the way, there'll be a value here as well. Okay, so let me just correct it. So, oops. So there will be value here. So I have just updated the values because obviously we need to have the basically attendance here as well, because obviously Q3 will attend to K3 as well. So this one block was missing. So yeah, it's updated now. So now we are saying that, hey, when we want to find the white cat sat on the, and if we are at this query, which is third, so it will only attend its previous tokens, and that's it. And Ansh Lamba, will it also attend its own token? Obviously. It is a common sense, but it will not create a much impact, because obviously you will get what you will get if you are just comparing cat with cat. But just for the understanding and for the, you can say, accuracy, yeah, you can say like it will attend to this thing as well, but it is not very, very important. It is important to just compare it with the previous tokens. Okay, makes sense. But yeah, it will attend it to previous the current one as well. Okay, the white cat sat on this thing. Now we have the softmax value. That means we have the relevancy score. That means now we know this cat token is 0.8. That means 80% relevant to this particular keyword, which is called white. Wow. Literally wow. This Q4 sat is 40% relevant on white and 50% relevant on cat. Okay. And 10% relevant on. Or basically, you can say the white cat sat. Okay, sat is like 10%. So there are these are like obviously arbitrary numbers, but you can just imagine like these are the normal numbers. So we are saying like, hey, this is just 50% relevant for this thing, and this is 40% relevant for this thing, and this is only 10% relevant for this particular key. So this way we have the relevancy score. We know like which token is more relevant, which token is less relevant, which token is contributing more context, which token is contributing less context. So we know the answer now. Now what we need to do, very simple thing, and my favorite because it is the last step. So what we do, once we have these relevancy scores, okay, now we simply need to multiply it with the normal embedding vectors. But before that, we simply find out one more variable, which is called value. Again, nothing special, very common thing. We will simply multiply our normal embedding vectors with some weights. Now, what kind of weights are these? These are the weights which enhances the values of each embedding. E3 will become V3. Simple, by applying a multiplication of weights to that particular embedding vector. Basically, in a nutshell, do not make a mess about these weights, because weights are just like, you can say, first of all, model specific. They simply try to add some features, some more, you can say, weights, like more spotlight to some area, so that they can just behave better. So they will add some weights so that they can just behave better as a value. When they just add weights or query, they can behave better as a query. When they add weights for, like, let's say, keys, they can behave better as features or keys. Just like that. Simple. Do not make it like, oh, it's a complex thing. No. So we have V as well. Okay, V3. So now what will happen? We have everything. We have value and we have relevancy score. Done. Simply do this. Literally do this. So now we need to find the delta context. Now what is this delta context? Obviously we are just finding the context. So this is a context called delta. So delta E3 will become V1, that means value of the first embedding, into 0.1. Why? Because it is only 0.1 relevant, 0.1 or basically 10% relevant for this particular, you can say, token, because this is E3. E3 is cat, right? The white cat. Cat is E3. So we are simply finding the context for cat only for now, and it is 90% relevant for white, and it will keep on doing the same stuff with all the other keys as well. Make sense? So this is the embedding, and let me show you if you are like not following up with the table. So we have this table, remember this table. So we are trying to find the context for E3. Let's say here. So I'll simply say delta of E3, okay, will become 0.1 into value. 0.1 into value. Value of what? E3. Okay. That means 10% of value, okay, of this one. Make sense? Then 0.8% of value of K2. K2 or basically E2. Make sense? This one. So here, let me just write it for you. It will become the white cat sat on, because it will help you to understand like what's going on. So what we're trying to say, we need to find the context for E3. So it will simply multiply 0.1 into the value of this, okay, because these are the values for here. So 0.1, 10% of the, 80% of white, wow, 80% of white, 10% of cat, okay. So it will become E3. 10% of the plus 80% context from white, okay, plus 10% context of cat. That's it. This is my context for cat. That is my E3. This is my context. This is the context. This is the context. Now you have the context. Now simply add this context into your original embedding. And I hope now the statement is obvious enough. Okay. Now what you need to do, final contextual embedding, which was our initial goal. We were supposed to find the E3 dash, which is a contextual embedding. So static embedding plus this context. And yes, we finally, after the long process, are able to find this context. Can you see the power of LLM? Like in order, see, you will be saying, hey bro, why it is a long process just to find the context? You are a human being, it is very easy for you to find the context. But it is a kind of magical thing that machines can understand the context with the help of transformers. Just look at it like this. It is like next to impossible thing. It was next to impossible thing because now it is possible. It was next to impossible thing, bro. How you are easily able to find the context like this? Literally wow. Literally wow. This is so good. So now what you need to do? You can simply perform the same step for all the other embeddings. So all these type of embeddings will be converted into contextual embeddings. Make sense? Make sense? Okay. Contextual embeddings. Okay, very good. Now, after finding the contextual embeddings for all of these things, let's go back to the major architecture. Okay, let's see what happens. So now these contextual embeddings will go to this LM head. Okay, and this LM head will only take the last tokens embedding. What? Yes, only the last tokens embedding. That means the white cat sat on the. Only the last token. Yes. Why? Because the last token has the context of all the previous tokens as well. Yeah, that's true. That's true. We have just seen that the token will only attend to the previous token. So the last token will always have the full context. So instead of using like all the tokens, it will simply use the last token like this, and it will display all the probabilities of the tokens. Make sense? So let's say it will say, bro, as per the vocabulary, I think you should use let's say sofa, and sofa's probability is like, let's say 70%, mat is like, let's say 20%, then table has like, let's say 10%. Okay, and there are other suggestions as well. So your model will pick by default will pick the token with the highest probability. So it will simply add sofa here. It will return sofa, and that sofa will go to the input text here for the next token generation. And you know the flow, like how it works, right? Make sense? So let me just show you graphically as well. So here this LM head will just give us all of these options, not like us, like to the model, and model will pick this word, highest probability sofa. Okay, now what will happen? This sofa will be attached here. Okay, again contextual embedding will be calculated for this as well. So it will be having contextual embedding like this. Okay, and then only this word, this last token, will be used to predict the next word. And let's say then we have whatever after the you can say, let me just check what was the response. So the response says like this. So the white cat sat on the whatever, okay, watching the golden and blah blah blah. So it will keep on doing this thing like generation, and then just predicting the next word, appending it to the input, and then just finding the probability for the best token available in the vocabulary. Simple. This is the whole process of it. This is the whole process of it. That is it. That is it. Ansh, Lamba, a quick question. Yeah, I know your question. You will say, Ansh, Lamba, is it like mandatory thing we have to pick the token with the highest probability every time? No, it depends upon the temperature. Oh, what temperature? What do you mean? So if you have ever used any kind of modern frameworks to build any GenAI application, you would have heard about temperature. Whenever we just initialize the model, we set the temperature. Temperature equals to 0.9, 0.8, 1, 0. What does it mean? So basically when we set temperature equals 0, that means we are saying model, do not be creative, just pick the token with the highest probability. Okay. When we say temperature equals 1, then we say model. You can be creative, and you can even pick the token with the low probability as well, just to see like what happens, because that's why it creates some creative content. So maybe it can pick this thing, table. The white cat sat on the table. Probability was less, but still it picked it because temperature is 1. So more the temperature is closer to 1, more creative it will be. More the temperature closer to 0, lesser creative it will be, but more, you can say, systematic and more, I wouldn't say accurate because nothing is wrong, but more systematic and more aligned towards following the rules. Hey, always pick the token with the highest probability, like this. Make sense? Make sense? Now let's read the research paper. What? No, don't worry. Not like read research paper, but we need to just have a quick look about the Decoder-Only Transformer as per the diagram available in the research paper. Okay, so let me just open that research paper. Transformers research paper. Yeah, perfect. So, okay, and view PDF. Okay, perfect. So this is basically the official research paper that you can also go and check and read it. Okay, so here we have a very beautiful diagram for this. Again, just a quick one. Just focus on this area. That's it. You do not need to focus on the left area because left is the encoder part. Okay, so do not worry about that thing. Okay, so and by the way, as I just mentioned, encoder decoder both were the first structure or architecture for transformers, but now we just use decoder only more with GPT models, but we will be just learning about all the things. But currently we are just focusing on decoder only because we have simply understood everything about decoder only. So let's confirm like everything is right or wrong. Okay, so first of all, as you know that our, basically you can simply write input here. Why? Because in case of decoder only, it will be our input. Okay, makes sense. So this is our input, right? And again, input embeddings. Why it is it an output, I will just tell you, don't worry, but I am just explaining you from the start. Input embedding. So what will happen? We will simply pass the text. Okay, this text will go here and it will be converted into static embeddings. As you can see, after converting it into the static embeddings, it will also get some positional encoding. See, yes. Then we are actually talking about masked multi-head self-attention. Ansh, Lamba, we have discussed masked self-attention in detail. What is this multi-head? So whatever we have discussed in the self-attention, it will be performed with multiple parallel heads. That means the same thing will be applied to multiple heads. Why? So let's take an example. Let's say you are in a sweet shop. Okay. On the day one, you focused more on the sweets. Okay, because you were hungry. After 2 days, you visited the same shop, literally same shop. You were focusing more on the price tag. This sweet is expensive. This sweet is like, okay, because you were not actually hungry, but you wanted to eat something and you also wanted to take care of the money. On the third day, you focused more on deals. Hey, do we have any kind of deals? If I just combine these two sweets, will I get some discount? So what are you doing? You are shifting your attention from one area to another. Even the shop is same, even the sweets are same, even everything is same, but you are shifting your attention, right? So whatever we have discussed it from the one side of attention. Maybe we are focusing more on the cat. In the second head, it will be more focusing on sat. In the third attention, it will be more focused on the white. So it will keep on shifting the focus. It will keep on shifting the attention. That's why we call it as multi-head self-attention. But steps, process, all those Q, K, V will be exactly same. But the thing is, it will keep on shifting the focus and that's it. not a big deal, okay? And it will be doing it in parallel. So nothing is actually stopping you to say, hey, what is masked multi-head self-attention? You know this, okay? Same thing, but it will be performed in parallel, okay? To just keep on shifting the focus. Make sense? Very good. Then what is this multi-head attention? Again, we need to do this? No. It will be coming directly from the encoder part, okay? This is called cross attention. After self-attention, we just call it as cross attention, but we are not using encoder part, so just ignore this. Then what is this feed forward? This is also called as FFN. Feed forward network, or basically feed forward neural network. So feed forward network will actually enrich our embedding. So whatever contextual embeddings we have, not we, like this transformer has produced, or basically transformer block has produced, it will enrich it. It will add some more things which are useful for predicting the next thing. Simply enriching part, that's it. Nothing fancy, just the enriching the contextual embeddings, like adding more things before just predicting the next word, okay? That's it. Like you can say, when you are just going to a sweet shop, everything is done, box is packed, but the shopkeeper just put the box inside a, you can say, any kind of bag, so that you can just easily handle it. That's it. The next, the last moment step, that's it. Now what is this linear and softmax? This is not softmax that we have just talked about here, because softmax here is softmax for doing that thing. Softmax is not actually any kind of special thing. It is just like normalizing your data, okay? This is also called as LM head. So once your embeddings are done, these both two things will be called as LM head, okay? LM head, simple. Why softmax? Because obviously when it will be just performing some linear transformations, okay, it needs to again be softmax. So it is a combined step, okay? But it is an LM head which is predicting the next token using probabilities. See, output probabilities. So now once it has predicted the next one, let's say it has predicted sofa. So now this sofa will be appended here in the input, and that is why it was written output, because it is actually the output, but now it is behaving as the input. Make sense? Understanding the chronology? Okay. So now sofa will come here, and again static embedding, position encoding, and same stuff. So it will keep on doing this thing, and that's how your GPT models work. Wow. Literally wow. Understood the concept? Understood the architecture? Just rewatch this part again, please. Because now after this, we're going to talk about encoder only part. And you know the best thing? We actually do not need to talk much about encoder only, because encoder only is much simpler than decoder only, and it is like only halfway of it. What is the difference between decoder only and encoder only? You already know the answer. The answer lies in the self-attention mechanism. Remember, in the decoder only, if my sentence is this, let's say the cat sat, or let's say the white cat sat on the. So let's say I'm just finding the contextual embedding for this token cat. It can only attend to these previous tokens like this, and these will be hidden or basically masked, these ones. But in case of encoder only, the only difference is this cat now can attend these tokens as well. Wow, that's it. Yes, that's it. Everything else is same. Wow. So what is the advantage if it can just, let's say, attend the next tokens? So first of all, why it can attend to the next tokens? Because it doesn't need to predict anything. It doesn't need to generate anything. It will simply understand the thing, understand the text. That's it. See, there's no output probabilities after this encoder. No. Encoder's task is just to have the better or richer understanding of the text of the input. Okay. So when we said the white cat sat on the, so now cat is having bidirectional context from left and from right, both. So it has better or richer understanding of the input. Oh, an encoder's task is just to have the better understanding of the text. That's it. It does not predict anything. It does not give you the output. It will not generate anything. It will simply have the better and richer understanding of the text. That is why all the contextual embedding, or you can say whenever you just want to store your data in the form of contextual embeddings, we simply use encoder only. Remember, we also saw the example of this thing of Google Colab, where we did not want to generate anything. We just wanted to understand our text. What is the meaning of our sentence? So we used actually encoder-only transformer, where we want to have a richer understanding or richer context for our input. That is it. This is the difference between decoder only and encoder only. Why I didn't discuss encoder only? Because you would be flipped. But now you are good. Now you are good. Now you are good, right? So let's quickly sum up decoder only and encoder only quickly. Okay, let's see. So now let's quickly discuss about encoder only transformers. I know like you now have a better understanding, but still we should touch it, right? Formally. Okay. So now if we just want to talk about encoder only transformer, it is nothing but transformers which are designed primarily for understanding and processing input sequences. Only and only understanding and processing input sequences, making them ideal for tasks such as text classification, sentiment analysis, namely named entity recognition. By the way, this is one of the popular ones, sentiment analysis. Okay, this is one of the popular ones. So let's say you are just working in an organization and that organization is selling some products. Okay, so you want to know the sentiment, the behavior of your customers, right? So there you will be using embeddings. Which embeddings? Embeddings from the encoder only transformer. Make sense? By architecture, it is exactly same as a decoder only transformer, but except one thing, it does not have the mechanism to generate the output sequences. Instead, it focuses on encoding the input data into rich contextual embeddings that can be used for various downstream tasks. Now, one of the most popular example of this transformer type is BERT. BERT. It is called bidirectional representational transformer, I think. Yeah, representation transformer, or maybe representational transformers. Why do we call it as bidirectional? You know the answer. Just think about it. Bidirectional means it can attend the tokens from both the directions, from left and right both. Remember, in decoder only it can only attend the previous tokens, but in encoder only it can attend the future tokens as well, or basically the next tokens as well. That is why it is called bidirectional. Oh, okay. And BERT models are very popular in the world of finding or creating the richer contextual richer embeddings, because it can understand the context better, because it is bidirectional. It is not just like attending only the previous tokens. Make sense? Okay, simple. Okay, very good. So this was all about encoder only transformers. Okay, now the last topic of this video is understanding encoder and decoder both. What if we just want to use encoder and decoder both, and where do we use it and how it works? Let me just explain it step by step so that you will not be confused. Okay, so let's see encoder decoder transformers. Okay, let's see. So now let's talk about the encoder decoder architecture. So basically, whenever we just talk about encoder decoder architecture, you need to be very careful. Okay, why? Because this can be a little bit confusing to you, but now it will be not, because you are not directly learning about encoder decoder. You have a very great understanding of decoder only. You have a very rich understanding of encoder only. Now it will be easier to understand the thing. And in order to understand this, I will directly take you the diagram, the official diagram of the research paper. Okay, because that is the best resource to have a look. So I will simply say transformers research paper and just go to view PDF. Okay, so you just need to follow my mouse. Okay, just for now. So first of all, as we know that this part left hand side, the smaller part is called encoder, This part is called decoder. So let me just tell you what will happen step by step. Okay. So let's say I said the white cat sat on the, okay. Let's say I want to, or just let's take a new example. Let's say, because why do we use encoder decoder? Because Ansh, Lamba, we use decoder only to generate the text basically in the GPT models. Makes sense. We use encoder only to find the richer embeddings. Makes sense. But where do we use encoder decoder both? Answer is very simple. Everywhere where the focus is on both the parts, understanding the input and generating the text. Okay, so where is that area? The area is in your day-to-day circle. It's called translation, right? Translation. Just tell me one thing. If you just want to translate something, let's say I am saying this. This is a red marker. I want to convert, or basically not convert, translate it in your, let's say, native language. Let's say Hindi, Telugu, any language, French, Spanish, any language. So just tell me one thing. Will you need richer contextual embeddings? Obviously, bro, because you need to translate one language into another language. You have to have the richer embeddings for each single alphabet, or basically each token, each word. Okay, so here you have to include encoder. Now, in order to generate something, let's say in Hindi, Telugu, Spanish, French, whatever, you need decoder because it will be generating token step by step. So in these kinds of areas, you use encoder decoder based transformers. And one of the very, very popular transformer which uses both encoder decoder, it's called T5. T5. Make sense? Okay. So now let's see how this will convert this thing in your native language. Okay, and you can all imagine what will be the translation in your native language. Okay, just keep this thing in your mind. Okay, just for a few seconds. Okay, so what will happen? What will happen? Step number one, this particular input will be converted into richer embeddings by encoder part. Okay, by encoder part. Because each token can attend all the other tokens, including previous and the next tokens. Make sense? So this will create the embedding of each token, and these embeddings will be richer embeddings. This will have like more context. Okay, and that's it. Yes, that's it. You need to store these embeddings just in your pocket for now. Okay, just keep it aside. Simple. You do not need to do anything. Just make the embeddings and that's it. Now, this input, our original input, will go to decoder part, and you know how it works. It will go token by token, okay, one by one, okay, and it will perform, first of all, masked multi-head attention. When it will be performing masked multi-head attention, it will find embedding for each word, right? So let's say we are finding the embedding for last token, marker, because last token is used to predict the next word. So let's say we have reached till the marker token. So now this marker token has embeddings, has richer, or basically contextual embeddings, not very much rich, but yeah, richer embeddings, normal, not very, very rich as compared to encoder, normal embeddings. Okay, but it has the context for previous tokens. Okay, so here it will be having contextual embeddings. Okay, contextual embedding of what? Marker, the last token. Okay, everything is fine. Now, when it will go further, here is the step where encoder will come into the picture. Encoder will say, bro, you have created contextual embedding. Decoder will say, yes. Okay, it's good. But do you know what? I have also created richer embeddings. You can use it to predict the next token with more accuracy. Decoder will say, oh really? Yeah, I would love to do that. So here one thing will happen, it's called cross attention. Cross attention. Simple. So it will simply say, bro, I can use your embeddings because I trust you. You are very pro in just creating embeddings and I can do that. I will definitely do that. Okay. So here what it will do, it will use the richer embeddings of the encoder and it will apply cross attention. Make sense? To improve the context created by decoder. And then it will go to feed forward network, basically enriching the same thing. Then LM head, and LM head will create a new token, which will be the output. So let's say this is a token called XYZ. And obviously it will be something in your language, because if you're just imagining, let's say in Telugu, it will be different. In Spanish, it will be different. So I simply wrote XYZ. Okay, very good. So now is the confusing part. Now you will say, okay, this token is predicted. Now this token will go to encoder part, or it will go to decoder part, or it will go to both the sides. So the answer is this new token will only and only go to the decoder part. Only and only go to the decoder part. Why? Why? Because this is the generator. Decoder is the generator. Encoder is not the generator. So it will only be appended here. Okay. Okay. So now XYZ's contextual embedding will be calculated. Okay. Then what will happen? It will again perform the cross attention. Even if it is not appending the token here, still it will use the richer embeddings of encoder at each iteration. In each iteration to use the richer embeddings. So every time it will perform cross attention, and then it will go to feed forward, and then it will go to LM head, and then it will, let's say, produce a new token called ABC. Okay, and then it will keep on adding the same thing. So in short, in encoder-decoder transformer, encoder's work is just to provide the richer embeddings, and that's it. That is it. It will never touch the new tokens. It will do nothing. Just provide the richer embeddings. That's it. The heavy lifting will still be done by decoder in encoder-decoder both. Make sense? Make sense? Make sense? And actually there are more models as well. Let me just show you T5 model. T5 model. So this is the full form, by the way, if you do not know. T5, text to text transfer transformer. Text to text transfer transformer. Basically, in short, they are just trying to say translations. Simple. Make sense? Make sense? Make sense? Make sense? And you can actually read about it if you just want to. T5 language model, text to text transfer transformer. So they are simply transferring one text to another text using transformer. Simple. Simple, simple, simple. I can also provide the this research paper in my GitHub repo so that you can just go and check it out. Okay. So this was all about your encoder-decoder transformer. And I can say, like, this is all about the transformers. And this is all about the large language models as well. Make sense? Make sense? Now, do you have good understanding of LLMs, of large language models, or transformers? Okay. Do you have the knowledge? Very good. But you made a promise. Okay. And you have to follow that. You will rewatch this section, basically the transformer section, for one more time at least, because it will be beneficial for you. Again, I'm repeating, I'm not saying this just for the sake of views. I am just saying so that you can learn and grow better. That is it. That is my end goal. Okay. So just rewatch this section for one more time. You will learn better. Why? You will understand better. You will keep those things in your mind. Trust me. Trust me. Okay. So I hope you enjoyed this video. I hope you loved this video. If so, please drop a lovely comment on this in the comment section, because I literally put so much of efforts to make this thing easy to understand, because I know LLMs are the future. I know you need to build fundamental knowledge in the world of LLMs as soon as possible, and now you have built the understanding. Now you are good to go to achieve your dreams and whatever, because obviously your base is ready, right, for the new wave of revolution in the industry. So like, it's your choice. Okay, I know my lovely fam will definitely drop a very lovely comment. I know, I'm sure. Okay, so if you love this video, just hit the subscribe button right now and just click on the video coming on your screen right now, and I will see you there. Bye bye.